Hello there, and welcome to Science for Sleep, the place where curiosity slows its pace, science speaks softly, and the universe feels just a little closer than it did a moment ago. Tonight, we're settling into a story that begins not with a bang or a bold claim, but with a careful glance outward toward a star system so close to us, astronomically speaking, that it has quietly occupied human imagination for centuries without ever truly revealing its inner life. Before we go any further, take a second to notice where you are right now. Maybe you're listening from a dim bedroom or a quiet living room, or somewhere in between moments, halfway to sleep but not quite there yet. What time is it where you are? Late evening, early morning, or that soft in-between hour where the day lets go and the night hasn't fully settled? Wherever you are, and whatever the clock happens to say, you're exactly on time for this. Tonight's gentle exploration begins with a familiar idea and an unfamiliar discovery. For generations, Alpha Centauri has been spoken of as our nearest stellar neighbour, a reassuring point of light that reminds us we're not floating alone in an endless dark. It's the closest star system to our own, close enough to feel almost reachable, yet distant enough to remain stubbornly mysterious. For a long time, it was something we could look at, measure, name, and map from the outside, but never truly understand from within. If you find this kind of slow, thoughtful wandering through science calming or helpful as you unwind, I'd quietly invite you to like the video or subscribe to the channel. It helps this space reach others who might be looking for the same gentle way to end their day. No pressure at all, just something to keep in mind as we continue. Now, when scientists talk about looking inside a star system, they don't mean opening it up like a machine or peering into a glowing core with a cosmic flashlight. They mean something more subtle, more patient. They mean tracing heat where it shouldn't linger, dust where it shouldn't settle, structure where earlier models insisted there should be none. And recently, using the James Webb Space Telescope, scientists were able to do exactly that with Alpha Centauri. What they found didn't overturn physics or rewrite everything we know about stars, but it did unsettle long-standing assumptions in a quiet, profound way. Alpha Centauri has always felt familiar. You may have heard of it in science fiction, in documentaries, or in passing conversations about where humanity might someday travel. It's often described casually as a single star, but that description has always been a simplification, a convenient shorthand for something far more complex. Even so, complexity alone doesn't usually shock scientists. What surprised them this time wasn't just what was there, but how clearly it appeared once the right kind of eye was finally turned in its direction. To understand why this matters, it helps to slow down and think about how we usually observe distant stars. Traditional telescopes capture visible light, the same kind your eyes use, just gathered more efficiently. That light tells us about brightness, motion, and surface temperature, but it leaves much of the surrounding environment invisible. Cold dust, faint debris, and subtle thermal structures don't shine brightly in visible wavelengths. They whisper in infrared instead, and until recently, our ability to listen to those whispers was limited. James Webb changed that. It wasn't designed to look farther in the traditional sense, but deeper in another way. It detects heat signatures so faint they would have blended into background noise for earlier instruments. It can separate overlapping sources of light with precision that allows entire systems to be studied as layered environments rather than simple points in space. When Webb turned its attention toward Alpha Centauri, it wasn't just observing stars. It was reading the quiet thermal fingerprints of everything around them. At first, the data didn't seem dramatic, a nearby star system behaving more or less as expected. But as the observations accumulated and the analysis grew more detailed, patterns began to emerge that didn't quite align with existing models. There were indications of dust structures that shouldn't have been stable, heat distributions that suggested ongoing processes rather than leftover remnants, and subtle asymmetries that hinted at motion and interaction where calm had been assumed. None of this appeared as a sudden revelation. There was no single image that made scientists gasp. Instead, the surprise unfolded slowly, the way understanding often does, as multiple independent signals began pointing in the same unexpected direction. Alpha Centauri, it seemed, was not the quiet, settled neighbour we once imagined. It was active in ways that forced a re-evaluation of how nearby star systems evolve over time. What makes this especially compelling is proximity. Discoveries like this are not unusual in distant systems thousands of light-years away. When strange structures show up around far-off stars, they can often be dismissed as exotic or unrepresentative. Alpha Centauri doesn't allow that comfort. It's too close, too familiar, too relevant. If something surprising is happening there, it raises the uncomfortable possibility that similar processes could be common, including around stars much like our own sun. As you listen, you might notice how this story doesn't rush toward conclusions. That's intentional. Science rarely moves in straight lines, and understanding unfolds gradually, shaped by uncertainty as much as by data. What Webb revealed inside Alpha Centauri wasn't a single answer, but a set of questions that scientists weren't expecting to ask, at least not yet. Questions about how dust behaves in mature star systems. Questions about whether planet formation truly ends as early as we once thought. Questions about how stable or dynamic nearby stellar neighbourhoods really are. These aren't the kinds of questions that keep you awake with excitement. They're the kind that linger gently, like background thoughts, reshaping understanding without demanding immediate resolution. In a way that makes them perfect companions for sleep. There's no urgency here, no cliffhanger that needs resolving before morning. Just a slow unfolding of curiosity, anchored in something real, something observed, something quietly surprising. When people hear the phrase nearer stellar neighbours, it can sound almost comforting, as if these stars are close enough to be familiar, predictable, or somehow well understood. In reality, proximity in space does not guarantee intimacy and knowledge. Even the closest star systems remain layered, complex environments that resist simple explanations, especially when viewed through the narrow slice of reality our instruments traditionally allowed us to see. Alpha Centauri sits just over 4 light-years away, a distance that is small by cosmic standards but still immense by human ones. Light leaving that system began its journey toward Earth more than 4 years ago, long before you pressed play, long before this day unfolded as it did. And yet, among the countless stars scattered across the Milky Way, Alpha Centauri remains the closest system beyond our own sun. It is the first destination mentioned when conversations drift toward interstellar travel, the benchmark against which other nearby stars are compared, and the reference point for imagining what the neighbouring solar system might look like if we could ever approach it directly. For centuries, our understanding of nearby stars was shaped almost entirely by visible light. Astronomers measured brightness, colour, position, and motion, building careful catalogues that mapped how stars moved relative to one another over long spans of time. From those measurements came estimates of mass, age, and temperature. These were impressive achievements, but they mostly described stars as isolated objects, glowing points set against a dark background. What lay around them, especially anything faint or cold, remained largely hidden. Alpha Centauri fit neatly into this picture. It was close enough to study in detail, yet stable enough to feel uneventful. Its motions were well tracked, its components were well named, its brightness was familiar. For a long time, it seemed like a system we already understood, at least in broad strokes. That sense of familiarity can be deceptive, especially in astronomy, where new tools often reveal that what looks simple was anything but. To take a quiet look toward Alpha Centauri is not just to point a telescope in its direction. It is to acknowledge how much context surrounds even the closest stars. This system is not a single sun hanging alone in space. It is a small stellar neighbourhood shaped by gravitational relationships that unfold over hundreds of thousands of years. The interactions between its stars influence everything around them, from the distribution of dust to the long-term stability of any planets that might be present. The two main stars, Alpha Centauri A and B, orbit each other in a slow, elegant dance. They are similar to our Sun in many respects, especially Alpha Centauri A, which has long been considered one of the best solar analogues we know. Alpha Centauri B is slightly smaller and cooler, but still well within the range of stars that could, under the right circumstances, host planets with familiar conditions. Then there is Proxima Centauri, the faint red dwarf that orbits much farther out, gravitationally linked to the pair but living a more solitary existence at the system's edge. This arrangement alone complicates any attempt to treat Alpha Centauri as a simple object. Multiple stars mean multiple gravitational influences, overlapping radiation environments, and a history shaped by mutual interaction. Any dust, debris, or planetary material within the system must navigate a shifting gravitational landscape, one that changes subtly over time as the stars move along their orbits. For many years, astronomers assumed that this complexity would make it difficult for delicate structures like dust disks or forming planets to survive for long. Especially in mature systems, it was thought that most of the material left over from star formation would either be swept away, locked into planets, or broken down by radiation and collisions. By the time a system reached the age of Alpha Centauri, which is estimated to be several billion years old, it was expected to be relatively clean and settled. That assumption shaped expectations. When scientists looked toward Alpha Centauri, they were not anticipating surprises. They were looking to confirm stability, to refine measurements, to use the system as a reference point for models built from observations of more distant stars. In many ways, Alpha Centauri was treated as a control sample, a nearby example of how a mature, Sun-like system should behave. The challenge, of course, was that many of the features scientists wanted to confirm were precisely the ones most difficult to observe. Coal dust does not glow brightly. Thin debris structures can be easily overwhelmed by the light of nearby stars. Subtle temperature variations blur together when resolution is limited. For decades, these limitations forced astronomers to infer rather than observe, to rely on models that filled in the gaps left by incomplete data. This is where the idea of looking inside begins to matter. To look inside a stellar neighbourhood is not to peer into a star's core, but to study the space between and around stars with enough sensitivity to detect what was previously invisible. It means measuring heat rather than light, structure rather than brightness, and patterns rather than points. James Webb was designed with this kind of observation in mind. Its instruments are tuned to infrared wavelengths, where cold material speaks most clearly. Dust grains warmed slightly by starlight emit faint infrared radiation. Thin disks of debris leave thermal signatures that can be mapped if the resolution is high enough. Subtle differences in temperature can reveal where material is concentrated, where it is sparse, and how it might be moving. When Webb turned its gaze toward Alpha Centauri, it did so without assumptions about what it should find. That is an important distinction. The telescope does not know what is expected. It records what is there as precisely as it can, leaving interpretation to the scientists who study the data afterward. What emerged from those observations was not a dramatic anomaly, but a quiet mismatch between expectation and reality. The infrared environment around Alpha Centauri appeared more structured than models predicted. Instead of a smooth, minimal background, there were indications of organized material, faint but persistent, arranged in ways that suggested ongoing processes rather than leftover noise. This was surprising not because it was spectacular, but because it was subtle and consistent. Subtlety is often more unsettling in science than obvious disruption. A single outlier can be dismissed. A quiet pattern that repeats across multiple observations is harder to ignore. To appreciate why this matters, it helps to consider how nearby stellar systems influence our understanding of distant ones. Astronomers often rely on nearby examples to calibrate their models. If a process appears common in a nearby system, it is often assumed to be common elsewhere. Conversely, if something seems absent close to home, it is easier to treat it as rare or exotic. Alpha Centauri has always played this calibrating role. Its closeness allows for detailed study that would be impossible for more distant stars. If our assumptions about its environment are incomplete or flawed, that has ripple effects across many areas of stellar and planetary science. Another reason this quiet look matters is psychological. There is a human tendency to associate familiarity with understanding. Alpha Centauri has been part of our astronomical awareness for so long that it can feel known, even when much of it remains unexplored. Discoveries made there feel more personal than similar findings in distant regions of the galaxy. They challenge not just scientific models, but our sense of cosmic orientation. As the data from Webb accumulated, scientists began to re-examine long-held ideas about how star systems age. The presence of structured dust or debris in a mature system suggests that processes thought to end early might persist far longer under the right conditions. It raises questions about collisions between leftover bodies, slow dynamical reshaping, or even the influence of unseen planets shepherding material into stable configurations. None of these possibilities need to be resolved immediately. In fact, part of the strength of this discovery lies in how many explanations remain open. The observations do not point to a single dramatic cause. They invite a broader reconsideration of how quiet, long-term evolution unfolds in systems that were once thought to be static. This shift in perspective aligns well with the broader theme of modern astronomy. Increasingly, the universe appears less like a collection of finished products and more like an ongoing process. Stars evolve, systems rearrange themselves, material moves, collides, settles, and resurfaces over timescales that stretch far beyond human experience. Alpha Centauri, despite its familiarity, is part of that story. It is not frozen in time, it is still changing, still responding to the forces that shaped it billions of years ago. The fact that we are only now beginning to see the finer details of that evolution speaks less to the system's secrecy and more to the limitations we have only recently overcome. When people first learn about Alpha Centauri, it is almost always introduced as a single destination, a lone star sitting just beyond our solar system, quietly glowing as the nearest point of light not called the Sun. That simplification is understandable. Human language prefers tidy labels, and the nearest star system sounds much cleaner than a gravitationally bound collection of stars with overlapping histories and long-term dynamical consequences. But the reality, as is often the case in astronomy, is richer and more complicated. Alpha Centauri is not one star. It never has been. It is a small family, a gravitational relationship that has endured for billions of years, shaping everything that exists within its reach. To understand why recent observations matter, and why looking inside this system produced unexpected results, it helps to slow down and really take in what this family looks like, how it formed, and how its members influence one another over immense stretches of time. At the heart of the system are two stars locked in a mutual orbit. Alpha Centauri A and Alpha Centauri B circle a common centre of mass, bound together by gravity in a slow, predictable rhythm. From a distance, they appear close enough to blend into a single bright point, which is partly why they were long treated as one object in early observations. Only with improved telescopes did astronomers realise they were watching a binary system, two stars dancing around each other rather than one star standing alone. Alpha Centauri A is the larger and brighter of the pair. In many ways, it is strikingly similar to our Sun. Its mass, temperature and luminosity place it comfortably in the category of Sun-like stars, which is one reason it has drawn so much attention over the years. When scientists look for familiar conditions elsewhere in the galaxy, stars like Alpha Centauri A are natural candidates. They burn hydrogen steadily, they live long lives, and they provide relatively stable environments over billions of years. Alpha Centauri B, while slightly smaller and cooler, is still very much a main sequence star. It too burns hydrogen in its core and emits a steady stream of light and heat. Though it differs from its larger companion, it remains close enough in character that the pair are often discussed together as near twins shaped by similar origins but following slightly different evolutionary paths. These two stars orbit each other at a distance that changes over time. At their closest approach, they are separated by about the distance between the Sun and Saturn. At their farthest, the gap widens to roughly the distance between the Sun and Pluto. This elongated orbit takes about 80 years to complete, meaning that over the course of a human lifetime the system subtly rearranges itself, even though those changes are far too slow to notice without careful measurement. This slow orbital motion has consequences. Gravitational interactions between Alpha Centauri A and B influence the space around them, carving out regions where material can remain stable and regions where it cannot. Any dust, debris, or potential planets within the system must exist in a constantly shifting gravitational environment, one that is shaped not by a single star, but by the combined pull of two. For a long time, this complexity led scientists to assume that Alpha Centauri's environment would be relatively clean. Binary systems were thought to be less hospitable to lingering debris, especially after the chaotic early stages of star formation had settled. Collisions, radiation pressure, and gravitational disturbances were expected to clear out most leftover material, leaving behind either well-formed planets or empty space. Then there is the third member of the family, one that complicates the picture even further. Proxima Centauri is a red dwarf star, much smaller and cooler than its two brighter companions. It does not orbit close to Alpha Centauri A and B in the way they orbit each other. Instead, it traces a wide, slow path around the pair, remaining gravitationally bound but distant, separated by thousands of astronomical units. For many years, Proxima's relationship to the system was debated. Was it truly bound, or merely passing by? Precise measurements eventually confirmed that it is indeed part of the family, loosely tethered to the central binary in a gravitational arrangement that may have persisted since the system's formation. That makes Alpha Centauri not just a binary system, but a triple one, with interactions unfolding on very different spatial and temporal scales. Proxima Centauri brings its own set of complications. Red dwarf stars are known for their activity. They flare frequently, releasing bursts of radiation that can dramatically affect nearby environments. Proxima, in particular, has been observed producing powerful flares that would be hazardous to life as we understand it on close-orbiting planets. Yet despite this volatility, Proxima hosts at least one confirmed planet, Proxima b, which orbits within what is often described as the habitable zone. The presence of Proxima b already challenged assumptions about where planets can exist and what conditions they can tolerate. But beyond planets, Proxima's role in the broader Alpha Centauri system raises deeper questions. Its gravitational influence, though weak compared to the central binary, still contributes to the long-term dynamical evolution of the system. Over millions or billions of years, even small influences can reshape orbits, stir debris, and alter the distribution of material. When scientists talk about looking inside Alpha Centauri, they're not looking at a static arrangement. They're observing a living system, one where gravity, radiation, and motion interact continuously. The small family metaphor is useful here, because like any long-lived family, the members influence one another in subtle but persistent ways. Early models of the system treated these stars largely in isolation, especially when it came to their surrounding environments. Alpha Centauri A and B were often modelled as if they existed in relatively empty space, with Proxima treated as a distant afterthought. This made calculations simpler, but it also glossed over interactions that, while slow, could accumulate meaningful effects over time. James Webb's observations have begun to expose the limits of those simplifications. When infrared data revealed structured material where smooth emptiness was expected, it forced scientists to reconsider how this family of stars interacts with its surroundings. Dust does not arrange itself arbitrarily. Its distribution reflects forces acting upon it, including gravity, radiation, pressure, and collisions. In a single star system like our own, these forces are relatively straightforward to model. Add a second star, and the equations grow more complex. Add a third, even a distant one, and long-term behavior becomes harder to predict. Resonances can form, stable zones can exist in unexpected places, material can be shepherded into rings or clumps rather than dispersed entirely. This is not to say that Alpha Centauri resembles a chaotic mess. On the contrary, its overall stability is precisely what allowed it to persist for billions of years. But stability does not mean simplicity. It means balance, and balance can involve intricate arrangements that only become apparent when observed with sufficient sensitivity. The family nature of Alpha Centauri also matters for another reason. It shapes how scientists think about planet formation in the system. Planets do not form in isolation. They emerge from disks of gas and dust that respond to the gravitational environment around them. In a system with multiple stars, those disks can be truncated, warped, or split into separate regions. The resulting planets may follow unusual orbits or form in places models once considered unlikely. For decades, the absence of clear planetary detections around Alpha Centauri A and B reinforced the idea that binary systems were poor places for planet formation. Proxima b stood as an exception, orbiting a star far enough from the central pair to avoid the worst of their gravitational influence. But absence of evidence is not evidence of absence, especially when observational limits are involved. Infrared observations sensitive to dust and debris provide indirect clues. Dust is a byproduct of collisions between larger bodies. Where there is dust, there are usually larger objects grinding themselves down over time. Detecting such material around Alpha Centauri suggests that the system may still host belts of debris, perhaps analogous to our asteroid belt or Kuiper belt, shaped by the combined influence of its stars. These possibilities are not conclusions, they are invitations to rethink. The small family that makes up Alpha Centauri appears to be more dynamically interesting than once assumed, and that interest grows precisely because of the system's age. This is not a young, chaotic environment still settling into place. It is an old system, one that has had billions of years to evolve, rearrange, and stabilize. Finding structured material in such a system challenges the idea that stellar neighborhoods inevitably grow quieter and emptier with time. It suggests instead that under certain conditions activity can persist, driven not by dramatic events, but by slow, ongoing interactions. As this picture becomes clearer, it also reframes how scientists think about our own solar system. The Sun, too, exists within a broader gravitational context, influenced by passing stars and the galactic environment. Studying Alpha Centauri as a family rather than a single object helps place our own cosmic neighborhood in perspective. The realization that our nearest stellar neighbors are not just nearby points of light, but a complex interacting family, sets the stage for understanding why James Webb's observations were so revealing. It explains why expectations built on simpler models may have missed important features. For most of human history, the problem was not a lack of curiosity, but a lack of tools. Long before astronomers wondered what might be hiding inside Alpha Centauri, they were already straining against the limits of what observation allowed. Even the closest stars remained stubbornly distant, their light reduced to points, their surrounding environments blurred into invisibility by distance, brightness, and physics itself. The inability to look inside was never due to indifference. It was the result of very real constraints that shaped what science could reasonably ask, let alone answer. To understand why Alpha Centauri's inner environment stayed hidden for so long, it helps to begin with something deceptively simple: contrast. Stars are extraordinarily bright. Anything near them, especially dust or faint debris, is not. When astronomers try to observe material close to a star, they are often fighting against overwhelming glare. It is similar to trying to see fireflies hovering near a stadium floodlight. The fireflies may be there, but the light overwhelms the eye. Alpha Centauri makes this problem worse, not better. Because it is so close to Earth, its stars appear especially bright in our sky. That brightness saturates detectors, washes out subtle signals, and makes it extremely difficult to isolate faint infrared emissions from surrounding material. Ironically, proximity, which is usually an advantage in astronomy, becomes a challenge when the objects you want to study are vastly dimmer than the objects you must look past to see them. Early telescopes, even sophisticated ground-based ones, simply did not have the sensitivity or resolution to separate these faint signals from stellar glare. Atmospheric interference further complicated matters. Earth's atmosphere absorbs and emits infrared radiation, precisely the wavelengths needed to detect cold dust and subtle heat signatures. This meant that from the ground, much of the information scientists wanted was either distorted or entirely inaccessible. Space telescopes improved the situation, but only gradually. Instruments like the Hubble Space Telescope revolutionized astronomy in visible and ultraviolet light. Yet Hubble was never designed primarily as an infrared observatory. While it could glimpse some infrared wavelengths, it lacked both the sensitivity and the thermal stability required to study faint, cold structures around bright nearby stars. Other infrared missions existed, but they faced their own limitations. Telescopes such as Spitzer opened new windows into the infrared universe, yet they were optimized for broader surveys rather than fine-grained studies of extremely nearby high-contrast systems. Their resolution was often insufficient to disentangle complex structures in crowded or bright stellar environments. They could detect excess infrared emission, hinting that dust might be present, but they could not map it in detail or confidently distinguish between different possible sources. This left scientists in an uncomfortable position. Models predicted certain outcomes. Observations hinted at others, but the gap between inference and direct evidence remained wide. In the case of Alpha Centauri, the prevailing assumption was that its environment had largely settled down long ago. Without clear data to challenge that view, there was little reason to push hard against it. Another barrier lay in how astronomical instruments handle heat. Infrared astronomy is essentially the study of warmth, and warmth is everywhere. Telescopes themselves emit infrared radiation. Their instruments glow faintly simply by existing at non-zero temperatures. For an infrared telescope to detect extremely faint signals, it must be kept incredibly cold. Colder than most natural environments, colder than space itself in some cases. Earlier missions could cool their instruments only so much. Mechanical cryocoolers, passive radiators, and limited supplies of a liquid coolant placed practical limits on how sensitive these telescopes could be and how long they could operate at peak performance. As the instruments warmed over time, their ability to detect faint infrared signals diminished. This mattered enormously for studying Alpha Centauri. The dust and debris scientists hoped to observe were expected to be cold, emitting only the faintest infrared glow. Detecting such emission required not just sensitivity, but stability. Even small temperature fluctuations in the telescope could overwhelm the signal entirely. Resolution posed another obstacle. Seeing inside a stellar system requires the ability to distinguish fine spatial details. In astronomy, resolution improves with telescope size. Larger mirrors gather more light and produce sharper images. For decades, space telescopes were constrained by the size of rockets that could launch them. Mirrors had to fit inside payload fairings, limiting how large they could be. James Webb broke this constraint by using a segmented mirror that could fold during launch and deploy in space. Before that innovation, no space telescope could offer the combination of mirror size and infrared capability needed to resolve faint structures around a system as bright and complex as Alpha Centauri. There was also a conceptual limitation at work, one that is less technical but equally important. Scientific expectations influence what scientists look for and how they interpret ambiguous data. For decades, the dominant narrative around mature star systems, especially binary ones, emphasized cleanliness and stability. The early chaos of star and planet formation was thought to give way to quiet equilibrium. Under that framework, Alpha Centauri was not a prime candidate for surprises. It was nearby, yes, but also old and well studied. Observing time on powerful instruments is limited and highly competitive. Scientists must make compelling cases for why a particular target deserves attention. When expectations suggest low likelihood of discovery, proposals are harder to justify. As a result, Alpha Centauri often fell into a category of known quantity, useful for calibration and reference, but not necessarily for uncovering new phenomena. That categorization subtly shaped research priorities. It did not prevent observation entirely, but it influenced the kinds of questions that were asked and the kinds that were left unpursued. Meanwhile, theoretical models reinforced one another. Simulations of binary star systems suggested that debris disks would be truncated or dispersed relatively quickly. Any remaining material would likely be sparse, diffuse, and difficult to detect. Without observational evidence to the contrary, those models remained largely unchallenged. It is worth emphasizing that none of this represents failure. Science advances by working within constraints, refining tools, and revisiting assumptions as new capabilities emerge. The inability to look inside Alpha Centauri earlier was not due to oversight or neglect. It was the natural outcome of technological limits intersecting with reasonable expectations. The turning point came not with a single breakthrough, but with the convergence of several advances. Improvements in detector technology made it possible to measure weaker signals with greater precision. Advances in cryogenic engineering allowed instruments to operate at unprecedentedly low temperatures for extended periods. Optical design innovations enabled large, deployable mirrors capable of resolving fine detail in infrared wavelengths. James Webb embodies all of these developments. Its mirror spans over 6 meters when deployed. Its instruments are shielded from the sun by a massive multi-layer sunshield, allowing them to cool passively to temperatures cold enough to detect faint infrared emission without being overwhelmed by their own heat. Its detectors are exquisitely sensitive, capable of distinguishing subtle differences in wavelength and intensity. Just as important, Webb operates from a location far from Earth, at the second Lagrange point, where gravitational forces and thermal conditions remain relatively stable. This stability reduces noise and allows for long, uninterrupted observations. For studying faint structures near bright stars, that stability is not a luxury. It is essential. With these capabilities in place, questions that once seemed impractical suddenly became approachable. Scientists could now propose observations that aim not merely to confirm existing models, but to probe their limits. Alpha Centauri, long treated as familiar territory, became newly interesting precisely because Webb could finally look past the glare and into the quieter spaces shaped by the system's long history. When Webb's observations were planned, they were designed cautiously. The goal was not to chase a headline, but to test sensitivity, validate techniques, and explore what might be possible. The expectation was not shock, but refinement. Yet as the data returned, it became clear that refinement alone would not suffice. The signals detected were subtle, but consistent. They did not appear as dramatic images suitable for immediate public release. They emerged through careful analysis, comparison across wavelengths, and repeated verification. This is often how the most meaningful discoveries unfold, not as sudden revelations, but as persistent discrepancies that refuse to disappear. In hindsight, it is tempting to ask why these structures were not anticipated more strongly, why models did not predict them more clearly. But models are built from what is known, and until Webb, what was known about Alpha Centauri's faint environment was limited. The system had been hiding in plain sight, not because it was intentionally elusive, but because our vision was incomplete. As understanding deepens, earlier limitations become easier to see. Brightness contrast, infrared noise, resolution constraints, thermal instability, and conceptual expectations all played their part. Together they formed a barrier that no single instrument could overcome alone. Only when multiple advances aligned did that barrier begin to dissolve. This shift does not mean that Alpha Centauri was misunderstood in every respect. Much of what scientists believed about its stars remains accurate. Their masses, ages, orbits, and general behaviour are well constrained. What has changed is the picture of the space around them, the quieter component that was once assumed to be simple or absent. That realization naturally leads to a deeper question. If our nearest stellar neighbour could conceal such complexity for so long, what else might be hiding in other systems we think we understand? And more specifically, what exactly did James Webb detect that prompted scientists to pause and reassess their assumptions? Built not as a replacement, but as a rethinking of how we observe the universe, the James Webb Space Telescope arrived with a quiet confidence that only comes from decades of careful planning. Its launch was dramatic, its deployment tense, but its purpose has always been patient rather than flashy. Webb was never meant to snap quick pictures and move on. It was designed to linger, to listen, and to notice what had been speaking softly all along. To appreciate why Webb matters so much in the context of Alpha Centauri, it helps to set aside the idea of telescopes as simple magnifying devices. Webb is not just a bigger eye, it is a fundamentally different kind of observer, tuned to aspects of reality that earlier instruments could barely sense, let alone interpret clearly. Unlike telescopes that focus primarily on visible light, Webb is an infrared observatory. That distinction is crucial. Visible light tells us what is hot, bright, and energetic. Infrared light tells us what is warm, cool, hidden, or obscured. It reveals dust clouds that block visible light, traces heat where stars no longer shine brightly, and uncovers structures that glow softly rather than blaze. Most of the universe does not shine in visible light. Stars do, but the environments around them often do not. Dust grains warmed slightly by starlight emit infrared radiation. Planets glow faintly with residual heat. Debris disks and leftover material whisper their presence through thermal signatures rather than brilliance. Webb was built to hear those whispers. At the heart of the telescope is its mirror, a segmented structure made of 18 hexagonal pieces coated in gold. When fully deployed, the mirror spans more than 6 meters across, making it the largest space telescope mirror ever launched. That size is not about prestige, it is about sensitivity and resolution. A larger mirror collects more light and can resolve finer details, both of which are essential for studying faint structures near bright stars. The mirror's segmented design was not an aesthetic choice, it was a necessity. No rocket fairing could accommodate a mirror of that size in one piece. Webb's mirror had to fold like a piece of origami, survive launch vibrations, and then unfold and align itself with extraordinary precision once in space. Each segment can be adjusted independently, allowing the telescope to fine-tune its focus to a degree that would have seemed implausible only a generation ago. But the mirror alone is only part of the story. Webb's instruments are what give it its unique voice. These instruments are sensitive across a range of infrared wavelengths, allowing scientists to analyze not just where heat is coming from, but what kind of material is producing it. Different substances emit infrared radiation in characteristic ways. By studying these patterns, scientists can infer composition, temperature, and structure without ever touching the objects themselves. This capability matters deeply when observing a system like Alpha Centauri. The material scientists hope to detect there is not bright, compact, or dramatic. It is diffuse, faint, and easily overwhelmed by stellar light. To separate such material from the glare of nearby stars requires both exquisite sensitivity and careful calibration. Equally important is Webb's thermal environment. Infrared telescopes must be cold, very cold. Any warmth from the telescope itself becomes noise, drowning out the signals astronomers want to measure. Webb addresses this challenge with one of its most distinctive features, a massive, multi-layer sunshield roughly the size of a tennis court. This sunshield blocks heat from the Sun, Earth, and Moon, allowing the telescope's instruments to cool passively to temperatures near absolute zero. On the sun-facing side, the shield can be heated to hundreds of degrees Celsius. On the instrument side, temperatures drop to levels cold enough that the telescope's own infrared emission becomes negligible. This thermal separation is what allows Webb to detect incredibly faint signals over long periods without interference. The location of the telescope also plays a role. Webb orbits the Sun at a point known as the second Lagrange point, or L2, roughly 1.5 million kilometers from Earth. At this location, the gravitational forces of the Sun and Earth balance in a way that allows the telescope to maintain a stable position relative to both. This stability reduces the need for frequent adjustments and minimizes thermal fluctuations, both of which are critical for sensitive infrared observations. From this vantage point, Webb can observe targets continuously without Earth repeatedly blocking its view. It can point steadily, collect data patiently, and build up signals over time. For studying faint dust around bright stars, this ability to integrate observations without interruption makes an enormous difference. When Webb was conceived, Alpha Centauri was not the headline target driving its design. The telescope was envisioned primarily as a tool to study the early universe, the formation of the first galaxies, and the atmospheres of exoplanets. Yet its capabilities naturally extended to nearby systems as well. In fact, proximity combined with faint structures creates some of the most demanding observational challenges, and Webb was built to meet challenges, not avoid them. Before Webb, attempts to study Alpha Centauri's surrounding environment were limited by contrast and noise. Observations could suggest excess infrared emission, but they could not localize it precisely or determine its structure. Was the emission coming from dust, from background sources, from instrumental artifacts? Without sufficient resolution and sensitivity, these questions remained unresolved. Webb changed the nature of the data. Instead of broad hints, it delivered spatially resolved information. Instead of ambiguous excess, it provided patterns. Scientists could now see where infrared emission was concentrated, how it was distributed relative to the stars, and how it varied across wavelengths. This is where the difference between seeing and understanding becomes apparent. Seeing a star is straightforward. Understanding the environment around it requires context, contrast, and patience. Webb provides all three. Another important aspect of Webb's design is its flexibility. The telescope can be configured for different observing modes, allowing scientists to tailor their approach depending on the target. Imaging reveals structure. Spectroscopy reveals composition. Time series observations reveal change. Together, these modes offer a multi-dimensional view of astrophysical systems. In the case of Alpha Centauri, this meant scientists could cross-check observations, ensuring that detected features were real and not artifacts of a particular instrument or method. Consistency across different wavelengths and observing modes strengthens confidence and reduces the risk of misinterpretation. It's also worth noting that Webb's data does not arrive fully formed. The raw signals are processed, calibrated, and analyzed through complex pipelines. Interpreting infrared data requires careful correction for background noise, detector behavior, and instrumental effects. This process is meticulous and often slow, but it is essential for extracting reliable information from faint signals. The early Webb observations of Alpha Centauri did not immediately announce themselves as surprising. At first glance, they appeared subtle, almost understated. It was only through careful comparison with models and previous expectations that the significance became clear. The system did not behave quite as it was supposed to. Webb's role here is not that of a dramatic revealer, but of a patient witness. It does not declare that something is wrong. It simply shows what is there with greater clarity than before. The shock, if that word applies, comes not from the telescope, but from the realization that long-held assumptions no longer fit the data. This realization underscores an important truth about scientific instruments. They do not just extend our senses, they reshape our questions. Once Webb demonstrated that faint structured infrared environments around nearby stars could be observed directly, it became impossible to ignore the implications. If Alpha Centauri could host such complexity, perhaps other nearby systems do as well. The arrival of Webb also altered the social dynamics of astronomy. Observing time on the telescope is precious and highly competitive. Proposals must be carefully justified, and targets must promise meaningful insight. As Webb began delivering unprecedented data, it became easier to argue that revisiting familiar systems with new eyes could be just as valuable as exploring distant exotic ones. Alpha Centauri benefited from this shift. No longer merely a reference point or calibration target, it became a laboratory for testing ideas about stellar environments, debris evolution, and long-term system dynamics. Webb did not just allow scientists to look inside, it made looking inside worthwhile. There is something fitting about this development. Our nearest stellar neighbours have always been part of our cosmic story, present in our skies and our imaginations, yet only now do we possess the means to see them in their full, environmental context. Webb did not bring Alpha Centauri closer, it brought our understanding closer. As the data continue to be analysed, Webb's observations serve as a reminder that familiarity can breed complacency. Even the closest stars can surprise us if we finally listen in the right way. The telescope's quiet success lies not in overturning everything we know, but in revealing that what we know has always been incomplete. With Webb now firmly in the picture, the question shifts from whether we can look inside Alpha Centauri to how we should interpret what we see. Rather than imagining a telescope peering through a glowing surface like a medical scan, it is more accurate to think of looking inside a star system as learning how to read its faintest signals. Nothing is being opened, sliced, or penetrated. Instead, scientists are listening to heat, tracing motion, and mapping patterns that emerge only when light too dim for human eyes is gathered patiently and interpreted carefully. A star system is not a solid object with an inside and an outside in the everyday sense. It is an arrangement of matter and energy spread across enormous distances, shaped by gravity and time. When astronomers speak about its interior, they are referring to the region around the stars, the space filled with dust grains, debris, gas, and sometimes planets, all interacting in ways that leave subtle but measurable traces. For much of astronomical history, this region was treated as empty by necessity. Stars dominated observations. Their light overwhelmed everything nearby. Anything that did not shine brightly enough was effectively invisible. As a result, star systems were often conceptualized as stars plus planets, with little attention paid to what lay in between unless it announced itself dramatically, as in the case of thick protoplanetary disks around very young stars. Looking inside a mature system like Alpha Centauri requires abandoning that simplification. It means acknowledging that space between stars is rarely empty. Even after planets form and the most obvious debris settles, there can remain a thin haze of material shaped by collisions, radiation, and gravity. This material does not glow brightly. It emits gently, in infrared wavelengths, carrying information about its temperature, distribution, and composition. Infrared light is the key. Everything with a temperature above absolute zero emits it. Warm objects emit shorter infrared wavelengths. Cooler objects emit longer ones. Dust grains warmed by nearby stars settle into a narrow thermal range, glowing just enough for sensitive instruments to detect. By measuring that glow across different wavelengths, scientists can infer how warm the dust is, which in turn provides clues about how far it is from the stars and how it is being heated. This is not guesswork. Physics tightly constrains the relationship between temperature, distance, and radiation. If dust appears warmer than expected at a given distance, it suggests additional heating or unusual properties. If it appears cooler, it may be shielded, clumped, or located farther out than assumed. These temperature maps become a kind of fingerprint for the system's structure. Looking inside also involves spatial resolution. It is not enough to know that dust exists. Scientists need to know where it is. Is it evenly distributed or concentrated in rings? Does it form a disk, a belt, or scattered clouds? Are there gaps that suggest the presence of planets clearing paths through the material? Each of these configurations points to different underlying processes. In systems like Alpha Centauri, this task is especially challenging because the stars themselves are so bright. Their infrared emission can drown out the faint signals from surrounding material. Advanced data processing techniques are required to subtract the stellar contribution accurately, leaving behind the subtle, residual glow that indicates dust or debris. This subtraction must be done with extreme care. Remove too little, and stellar glare contaminates the signal. Remove too much, and real features vanish. The process relies on precise models of stellar emission, informed by independent measurements and validated across multiple wavelengths. Only when the residuals behave consistently can scientists trust that they are seeing something real. Another important aspect of looking inside is time. Star systems are not static snapshots. Over time, dust grains collide and fragment. Radiation pressure pushes small particles outward. Gravity shepherds material into resonant orbits. By comparing observations taken at different times, or by studying how material must behave to remain stable, scientists can infer whether what they see is transient or long-lived. A stable structure suggests ongoing processes maintaining it. An unstable one suggests recent events, such as collisions between larger bodies. In mature systems, persistent dust often points to continuous replenishment, meaning that something is still actively producing it. This is one of the reasons unexpected dust around Alpha Centauri drew attention. It implied activity where quiescence was expected. Looking inside also means interpreting absence. Regions where no dust is detected can be just as informative as regions where it is present. Clear gaps may indicate planets sweeping up material. Sharp edges may point to gravitational boundaries imposed by stellar motion. Gradual fall-offs suggest different dynamics than abrupt cut-offs. None of this involves direct imaging of planets or debris in the way people often imagine. The process is indirect but rigorous. Scientists assemble a coherent picture by combining thermal data, spatial distribution, and physical modelling. Each piece alone is ambiguous. Together, they form constraints that narrow the range of possible explanations. In the context of Alpha Centauri, this approach revealed something subtle but important. The infrared signatures did not match those of a system that had completely settled. The distribution of heat suggested structured material rather than a uniform background. The temperatures implied dust located in regions that models had predicted would be unstable over long timescales. This mismatch forced a re-evaluation of what stability means in a multi-star system. Stability does not necessarily imply emptiness. It can also mean dynamic equilibrium, where material persists because the forces acting on it balance out over time. In a binary or triple system, such balances can occur in unexpected places. Looking inside therefore becomes an exercise in humility. It requires acknowledging that previous models were based on incomplete data. It demands careful separation of observation from assumption. It also rewards patience, because the signals involved are faint and the interpretations nuanced. Another layer of meaning comes from composition. Infrared spectroscopy allows scientists to identify characteristic absorption and emission features associated with specific materials. Silicate dust, for example, leaves a distinct imprint. Carbon-rich compounds behave differently. Ice-coated grains emit differently than bare ones. By examining these features, scientists can infer what the dust is made of, which in turn provides clues about its origin. Material left over from planet formation has a different signature than material produced by recent collisions. Over time, radiation alters surfaces, changing their spectral properties. Reading these changes is part of looking inside. This compositional information is particularly valuable in nearby systems. Because Alpha Centauri is close, Webb can collect higher quality data than it could for similar structures around distant stars. That improves confidence and allows finer distinctions between competing explanations. Looking inside also involves context. No star system exists in isolation. The galactic environment matters. Passing stars, interstellar material, and long-term gravitational influences can all shape a system's outskirts. For Alpha Centauri, its motion through the galaxy and its interactions over billions of years contribute to its present configuration. By studying its internal environment, scientists can place Alpha Centauri within a broader evolutionary framework. Is it typical of Sun-like systems? Or does its multi-star nature produce distinct outcomes? Answering these questions helps refine our understanding of stellar neighborhoods more generally. It is worth emphasizing what looking inside does not mean. It does not mean finding dramatic movie-like structures. It does not mean discovering glowing worlds on the verge of contact. The findings are quiet, incremental, and deeply technical. Their significance lies in how they challenge expectations, not in how they appear. For a listener winding down, this process may seem almost meditative. Scientists waiting for signals, subtracting noise, testing models, and slowly converging on understanding. There is no rush. The system has existed for billions of years. Taking a few extra months or years to understand it properly is not a problem. This slow pace is a feature, not a flaw. It allows discoveries to mature, interpretations to be refined, and errors to be caught before conclusions are drawn. It also means that when something unexpected persists through repeated analysis, it carries weight. In Alpha Centauri's case, the unexpected persistence of structured infrared emission suggests that our picture of nearby star systems needs adjustment. Looking inside revealed not chaos, but complexity. Not dramatic upheaval, but quiet activity continuing long after models predicted it would fade. This realization opens the door to deeper questions. If dust and debris can persist in such a system, what mechanisms support them? Are there unseen planets shaping the environment? Are collisions ongoing at low levels? Are binary dynamics more accommodating than once thought? At first, nothing about the data looked dramatic. There was no sharp outline, no obvious ring glowing clearly against the dark, no immediate feature that leapt out and demanded attention. The infrared glow surrounding Alpha Centauri appeared subtle, almost hesitant, the kind of signal that could easily be dismissed if one were not already looking carefully. And that in many ways is exactly why it mattered. Infrared astronomy rarely announces itself loudly. It works in gradients, in faint excesses, in small deviations from what models predict should be there. When scientists began examining the infrared measurements from James Webb pointed toward Alpha Centauri, they were not expecting surprises. They were validating techniques, refining baselines, and checking whether the telescope behaved as expected when observing an extremely bright nearby system. What they found instead was something slightly, persistently off. The first clue came from excess emission. In simple terms, the system appeared to be glowing just a little more in certain infrared wavelengths than it should have been if only the stars themselves were contributing. This kind of excess is not unusual in astronomy. It can come from background galaxies, instrumental noise, calibration errors, or interstellar dust unrelated to the system being studied. Each of these possibilities had to be ruled out methodically. Background sources were the easiest to address. Alpha Centauri's proximity means its apparent motion across the sky is relatively fast compared to distant stars and galaxies. By comparing observations taken at different times, scientists could distinguish between features that moved with Alpha Centauri and those that remained fixed in the background. The excess emission moved with the system. That immediately ruled out distant galaxies or unrelated background structures. Instrumental artifacts were next. Webb's detectors are exquisitely sensitive, but sensitivity comes with complexity. Every detector has quirks, noise patterns, and subtle behaviours that must be understood. Calibration teams compared the Alpha Centauri data with observations of other bright stars known to lack surrounding dust. The patterns did not match known artifacts. The excess emission persisted even after aggressive correction and cross-checking. Interstellar dust posed a more nuanced challenge. The space between stars is not empty. It contains diffuse material that can emit infrared radiation. However, interstellar dust tends to be relatively smooth on the scales Webb was observing. The glow detected around Alpha Centauri was not uniform. It showed structure, variations in intensity that hinted at organisation, rather than a random foreground or background haze. Once these alternatives were excluded, the implication became harder to avoid. The infrared glow was associated with Alpha Centauri itself. The next step was to examine the spectral characteristics of the emission. Different materials emit infrared radiation in different ways. By looking at how the intensity changed across wavelengths, scientists could infer whether the glow was consistent with dust, gas, or something else entirely. The signature aligned most closely with thermal emission from dust grains warmed by starlight. That alone would not have been shocking if Alpha Centauri were a young system. Young stars are surrounded by thick disks of gas and dust left over from their formation. But Alpha Centauri is old, billions of years old. Any primordial disk should have dissipated long ago, either accreted into planets or blown away by radiation and stellar winds. The unexpected element was not the presence of dust, but its apparent persistence and organisation. Temperature estimates added another layer to the puzzle. The dust appeared to be neither extremely hot nor extremely cold. Its inferred temperature placed it at distances from the stars where long-term stability was considered unlikely, given the system's binary nature. In a single-star system, such regions might host asteroid belts or debris disks. In a close binary, gravitational perturbations were expected to disrupt such structures over time, yet the data suggested otherwise. The glow was not symmetrical in the simplest sense. Its distribution varied depending on direction relative to the star's orbit. That asymmetry was subtle, but consistent across observations. It hinted at material shaped by gravitational influences rather than randomly distributed dust drifting through space. At this point, scientists began comparing the observations to simulations. Existing models of binary star systems predicted certain zones of stability, where material could persist, and other zones where it would be rapidly cleared out. The infrared emission did not align neatly with those predictions. It appeared in regions that models had marked as dynamically hostile. This mismatch did not immediately invalidate the models. Instead, it suggested that additional factors might be at play. Perhaps the dust grains were larger than assumed, making them less susceptible to radiation pressure. Perhaps collisions between larger bodies were continuously replenishing the dust, maintaining a steady-state glow. Perhaps unseen planets were shepherding material into stable configurations through resonant interactions. Each possibility carried implications. Continuous replenishment would imply ongoing collisions among larger bodies, like asteroids or planetesimals. That would mean the system still harbours a population of solid objects actively interacting far longer than expected. Shepherding by planets would imply the presence of planets that have not yet been detected, influencing the dust indirectly. The data alone could not distinguish between these scenarios definitively. What it could do was demonstrate that something was happening. The system was not as inert as previously thought. Another aspect of the signal that drew attention was its consistency across wavelengths. Infrared emission from dust changes predictably with wavelength depending on grain size and composition. The observed spectrum suggested a relatively narrow range of grain properties. This hinted at a common origin rather than a random mix of materials. Such uniformity is often seen in debris disks produced by collisional cascades. Larger bodies collide, producing fragments. Those fragments collide again, grinding down into smaller particles until radiation pressure removes the smallest grains. The result is a population of dust with characteristic sizes and emission properties. If Alpha Centauri hosts such a cascade, it would imply an active debris environment comparable in some respects to our own asteroid belt or Kuiper belt, though shaped by a very different gravitational context. Spatial analysis added further intrigue. The emission appeared confined to specific regions rather than spread evenly around the stars. This confinement suggested structure. Structure implies influence. Influence implies agents, whether gravitational or collisional. Importantly, the signals were weak. This was not a massive luminous disk. It was a faint glow, just strong enough to register above noise. That faintness explains why it had escaped detection for so long. Earlier instruments simply could not see it, and even with Webb, extracting the signal required careful analysis. The shock, if it can be called that, came not from drama, but from persistence. Each test designed to make the signal go away failed. Each alternative explanation fell short. The glow remained. In science, that is often the moment when curiosity deepens, not because an answer has been found, but because the question has changed. Instead of asking whether Alpha Centauri has a debris environment, scientists began asking how such an environment could exist and what it says about system evolution more broadly. The unexpected signals also prompted a re-examination of earlier data. Older infrared observations, once considered too noisy or ambiguous to interpret, were revisited in light of Webb's clarity. In some cases, faint hints that had been dismissed as artifacts now appeared suggestive. Webb did not just add new data, it reframed old data. This reframing has broader implications. If a nearby, well-studied system like Alpha Centauri can harbour faint but structured dust, undetected for decades, similar features could exist around other stars, especially those slightly farther away where detection is even harder. The universe may be dustier, more active, and more complex than previously assumed. For listeners easing towards sleep, this might sound like a story of uncertainty rather than discovery. That is accurate. Science often advances not by replacing certainty with certainty, but by replacing assumed certainty with informed uncertainty. The infrared glow did not provide clear answers, it removed comfortable ones. There is something quietly humbling about that. Even our closest neighbours can surprise us when we finally look carefully enough. The signals Webb detected were always there, warming dust grains, radiating gently into space. They did not suddenly appear. Our ability to notice them did. As analysis continues, scientists are cautious. Claims are framed conservatively. Language remains measured. The glow is described as consistent with debris, suggestive of structure, indicative of ongoing processes. Definitive statements are avoided, not out of hesitation, but out of respect for complexity. Yet the implications ripple outward. If Alpha Centauri hosts a persistent debris environment, it affects how scientists think about planet formation, long-term stability, and the evolution of multi-star systems. It also affects how future observations are planned. Targets once considered low priority may be revisited with fresh interest. There is also a philosophical dimension, subtle but present. Alpha Centauri has long been imagined as a potential destination, a place where future probes or even distant descendants of humanity might one day travel. Understanding its environment matters not just scientifically but imaginatively. A dusty dynamic system feels different from a clean static one. The unexpected infrared signals do not tell us everything. They do not reveal planets directly. They do not show dramatic structures. What they do is open a door. They invite deeper investigation, more refined modelling, and continued observation. Instead of fading smoothly into the background the way long-settled systems are supposed to, the material around Alpha Centauri began to reveal a shape. Not a sharp outline or a dramatic ring that could be pointed to in a single image, but a persistent arrangement that emerged only when data were layered carefully, wavelength by wavelength, assumption by assumption. What made this arrangement so unsettling was not its brightness, but its location and coherence. According to prevailing models, it simply should not have been there. To understand why this mattered, scientists first had to revisit what should exist in a system like Alpha Centauri. In mature star systems, especially those with multiple stars, dust is expected to be scarce. Early in a system's life, dust is abundant. It forms disks, clumps, and filaments as planets begin to assemble. Over time, that dust either becomes part of larger bodies or is removed by radiation pressure, stellar winds, and gravitational disturbances. Billions of years later, what remains is usually thin, diffuse, and difficult to detect. Binary systems accelerate this clearing process. Two stars orbiting one another create gravitational instabilities that disrupt delicate structures. Regions that might be stable around a single star become chaotic when a second star's influence is added. Dust grains are perturbed, their orbits stretched and twisted until collisions grind them down or radiation pushes them out of the system entirely. The expectation, supported by decades of simulations, was that Alpha Centauri's inner regions would be largely clean. Yet Webb's infrared data told a different story. When scientists mapped the intensity of infrared emission around Alpha Centauri A and B, they found concentrations that did not align with a smooth, featureless decline. The glow varied with distance in a way that suggested material was not evenly dispersed. There were hints of belts or zones where dust density increased rather than decreased. These zones appeared in regions where long-term stability was considered unlikely. This is where light becomes a diagnostic tool rather than a simple signal. Infrared light does not just say that something exists, it says how warm it is, and temperature in space is closely tied to location. Dust closer to a star is warmer, dust farther away is cooler. By modelling how the observed infrared emission corresponded to temperature, scientists could estimate where the dust must be located. Those estimates place the dust in intermediate regions, not tightly bound to either star, but not far enough out to be immune to their combined gravitational influence. In simulations, material in those regions tends to be short-lived. Orbits become unstable. Grains collide or are ejected. Over long timescales, such regions are expected to empty out. And yet, there it was. The structure did not resemble a primordial disk which would be thick and massive, nor did it resemble random interstellar dust, which would be diffuse and uniform. Instead, it looked like a debris structure, maintained over time by ongoing processes rather than inherited from the system's birth. This distinction matters. A primordial disk is a remnant of formation. A debris structure is a sign of activity. It implies collisions, replenishment, and motion. It implies that larger bodies are still present, interacting, and slowly grinding themselves down into smaller fragments. Dust does not last long on cosmic timescales. Individual grains are ephemeral. They are pushed by light, heated, eroded, and eventually expelled. If dust is present in a mature system, it almost always means that something is making more of it. That something is usually collisions between larger solid objects. In our own solar system, this process occurs in the asteroid belt and the Kuiper belt. Asteroids collide, producing dust that forms a faint zodiacal cloud. Comets shed material, adding to the haze. This dust glows faintly in infrared, detectable to sensitive instruments. The key difference is that our system has a single dominant star, and the regions where debris persists are well understood. Alpha Centauri complicates that picture. Two Sun-like stars orbiting each other create overlapping gravitational zones. Stable regions exist, but they are narrower and more complex than in single-star systems, Models predict where debris belts might survive, but those predictions depend sensitively on assumptions about masses, orbits, and initial conditions. The structures inferred from Webb's data did not line up neatly with the most conservative of those predictions. That does not mean the predictions were wrong in principle. It means reality may be exploiting corners of parameter space that models had not emphasized. Another possibility scientists considered was shepherding by planets. Planets can carve gaps in debris disks, trap dust in resonances, and maintain sharp edges that would otherwise blur away. In multi-star systems, planets themselves can occupy unusual orbits, influenced by more than one stellar mass. Such planets might be difficult to detect directly, especially if they are relatively small or located in challenging observational regions. If unseen planets are shaping Alpha Centauri's dust, that would be a significant finding in its own right. It would suggest that planet formation around Alpha Centauri A or B may have been more successful than previously thought, despite the system's binary nature. It would also imply that planets could survive and influence their environments over billions of years in ways models had underestimated. Alternatively, the dust structures could be maintained by a balance of forces rather than discrete shepherds. Radiation pressure pushes small grains outward. Gravity pulls them inward. Collisions break larger bodies into smaller ones. In certain configurations, these forces can balance in ways that allow dust to linger longer than expected, especially if replenishment is steady. The observed structures were not dramatic enough to point clearly to one explanation over another. That ambiguity is part of what made them compelling. They resisted easy classification. They sat at the edge of expectation, neither completely forbidden nor comfortably predicted. Light itself played a role in shaping the structures. Radiation from Alpha Centauri A and B exerts pressure on dust grains. Smaller grains are more affected than larger ones. Over time, this pressure can sort dust by size, creating spatial variations in emission. The infrared glow detected by Webb may reflect such sorting, revealing zones dominated by particular grain sizes. This interpretation fits with the spectral data, which suggested a relatively narrow range of grain properties. It also fits with the idea of ongoing collisional cascades producing dust that is then filtered by radiation forces. Still, the presence of structure remained the central puzzle. Structure implies organization. Organization implies sustained influence. In a system where chaos was expected to dominate, organization demands explanation. The phrase "shouldn't be there" does not mean impossible. It means unexpected given what we thought we knew. Science advances precisely through such moments. When observation and expectation diverge, either the observation is flawed or the expectation is incomplete. In this case, repeated checks strengthened confidence in the observation. As scientists discussed the findings, caution dominated the language. No one claimed discovery of a specific belt or disk without further confirmation. Instead, they spoke of excess emission, spatial variation, and consistency with debris structures. This careful phrasing reflects both the complexity of the data and the high standards of the field. There was also an awareness that Alpha Centauri's brightness made interpretation harder, not easier. Subtle errors in subtracting stellar light could create artificial structures. To address this, teams compared independent reductions, varied assumptions, and tested how sensitive the inferred structures were to different processing choices. The patterns persisted. That persistence is what gave the result weight. When multiple approaches converge on the same conclusion, confidence grows, even if the conclusion itself remains provisional. The structures also raise questions about timescale. If debris is present, how long has it been there? Is this a recent development triggered by a collision event, or a long-lived feature maintained over billions of years? The data alone cannot answer this directly, but they constrain possibilities. A recent catastrophic collision would produce a surge of dust that would decay over time. A steady-state debris environment would produce a more constant signal. The relatively smooth spectral properties suggest the latter, though this remains an area of active investigation. There is something quietly profound about finding such complexity so close to home. Alpha Centauri has been studied for centuries. Its stars have been tracked, named and characterized in exquisite detail. Yet the space around them, the quieter component of the system, still held surprises. This serves as a reminder that stars are not isolated beacons in empty space. They are embedded in environments shaped by their histories and interactions. Those environments can persist long after formation, quietly evolving in ways that challenge simplified narratives. As listeners drift further into the story, it may feel as though the focus is narrowing, becoming more technical. That narrowing is part of the process. Understanding why these structures matter requires patience and attention to detail. There is no single dramatic revelation, only a gradual accumulation of evidence. The dust around Alpha Centauri does not announce itself loudly. It glows softly, persistently, asking questions rather than answering them. Its presence suggests that nearby star systems may be more active and more varied than we have allowed ourselves to imagine. Beneath the discussion of dust and infrared light, a quieter implication began to take shape, one that scientists approached cautiously, almost reluctantly. Dust on its own is interesting, but dust with structure carries a suggestion that is hard to ignore. It hints at the presence of larger bodies, objects massive enough to shape their surroundings without announcing themselves directly. In other words, it hints at worlds, or at least at the building blocks and remnants of worlds, still playing an active role in a system once thought to be long settled. It is important to be clear about what this does and does not mean. No one is claiming that James Webb has directly observed planets forming around Alpha Centauri A or B. There are no crisp images of spinning proto-worlds or glowing planetary disks. The hints are indirect, subtle, and rooted in dynamics rather than imagery. But in astronomy, indirect evidence is often the most powerful kind, especially when it persists across multiple lines of analysis. To understand why dust can point toward worlds, it helps to consider how planetary systems evolve over time. In the earlier stages, young stars are surrounded by thick disks of gas and dust. Within those disks, tiny grains collide and stick together, gradually forming larger aggregates. Over millions of years, those aggregates grow into planetesimals, then into planets. During this phase, dust is abundant and obvious. As planets form and the system matures, that original disk disappears. Gas is blown away by stellar radiation. Dust is either incorporated into planets or removed. What remains, if anything, is a debris environment, sustained not by formation, but by destruction. Collisions between leftover bodies grind material down into dust, which then emits infrared radiation until it is pushed out of the system. In mature systems, debris structures are usually associated with populations of solid objects. Asteroid belts, Kuiper belts, and scattered disks are all examples of this process. They are not places where planets are forming from scratch, but places where the remnants of formation continue to interact. Alpha Centauri was expected to fit this latter category only weakly, if at all. Its binary nature led many models to predict that stable reservoirs of debris would be small or non-existent, especially close to the stars. If debris were present, it was expected to be confined to narrow, well-defined regions or dispersed entirely. The infrared signals Webb detected complicate the expectation. The dust appears neither extremely confined nor entirely diffuse. Its inferred location suggests that it exists in regions where gravitational influences overlap in complex ways. Maintaining material there over long timescales likely requires more than chance. This is where the idea of unseen worlds enters the discussion. Planets are efficient sculptors of their environments. Even when they cannot be seen directly, their gravitational influence can be inferred from the patterns they leave behind. Rings, gaps, clumps, and asymmetries in dust distributions often point to planetary companions shaping the flow of material. In our own solar system, the structure of the Kuiper belt reflects the presence of Neptune. Resonant populations of objects occupy specific orbital relationships, maintained over billions of years. Without Neptune, those structures would not exist. The dust produced by collisions among these objects carries the imprint of that architecture. Applying this logic to Alpha Centauri is tempting but fraught. Binary systems complicate everything. A planet orbiting one star must contend with the gravitational pull of the other. Stable planetary orbits exist, but they occupy restricted zones. If planets exist in Alpha Centauri, their influence on dust would be layered on top of the star's influence, producing patterns that are harder to predict and harder to recognize. Still, the observed structures suggest organization rather than randomness. Organization implies guidance. Guidance implies mass. Another possibility is that the system hosts belts of planetesimals, analogous to asteroid belts, maintained in stable zones defined by the combined gravitational field of the stars. These belts could persist over long periods, slowly grinding down and replenishing dust. Such belts would not require planets to exist, but they would represent a population of solid bodies that survived the system's turbulent early history. Survival itself is noteworthy. In many models, binary star systems disrupt planetesimal formation and retention. Finding evidence for long-lived solid populations in Alpha Centauri would suggest that planet formation, or at least planetesimal formation, is more robust in such environments than previously believed. The phrase, "world still taking shape," should therefore be understood broadly. It does not necessarily mean planets actively forming today. It can mean that the system is still dynamically active, that its architecture continues to evolve, and that solid bodies continue to interact in ways that shape the environment. There is also the possibility of late-stage planet formation. While most planet formation occurs early, some processes can extend much longer. Collisions between large bodies can create new fragments. Migration of planets can destabilize reservoirs of material, triggering renewed activity. Binary star interactions can change over time as orbits evolve, opening or closing stable zones. Alpha Centauri's long orbital period means that its gravitational configuration changes slowly but significantly over decades and centuries. Over billions of years, these changes could have cumulative effects, stirring material that had once been quiescent. Webb's observations do not show active accretion disks, but they do not rule out ongoing reshaping. The dust's presence suggests a system that is not frozen. It suggests motion, interaction, and renewal. There is also the context of Proxima Centauri to consider. Proxima hosts at least one confirmed planet, Proxima b, and possibly others. Its existence demonstrates that planet formation occurred somewhere in the system despite its complexity. While Proxima is distant from Alpha Centauri A and B, the system likely formed from the same molecular cloud. Shared origins can lead to shared tendencies. If planet formation was possible around Proxima, it may also have been possible around the central binary, even if the outcomes differed. The dust structures around Alpha Centauri A and B could be the remnants of such processes, shaped by subsequent evolution rather than erased entirely. Another subtle hint comes from the scale of the emission. The amount of dust inferred is small, far less than in young systems, but not negligible. This places Alpha Centauri in a category similar to debris disk systems, observed around other mature stars. Such systems often host planets, though the relationship is not one-to-one. Statistically, debris disks are more common around stars known to host planets. This correlation does not prove causation, but it suggests that the processes that lead to planet formation also leave behind debris environments that persist. If Alpha Centauri shows signs of a debris environment, it nudges probability toward the presence of planets, even if they remain undetected. detection itself is challenging. Alpha Centauri's brightness makes direct imaging of planets difficult. Radial velocity measurements, which detect planets by the wobble they induce in their host star, are complicated by stellar activity and by the presence of the second star. Transit methods, which detect planets passing in front of their stars, require precise alignment and long monitoring. In other words, the absence of confirmed planets around Alpha Centauri A and B does not strongly constrain their existence. It constrains our ability to see them. Dust, in this context, becomes a messenger. It tells us that solid material exists and that it's interacting. It suggests that the system's architecture includes more than stars and empty space. It opens the door to the idea that worlds, in some form, are part of the picture. There is also a conceptual shift involved. For a long time, planet formation was treated as a brief chapter at the beginning of a system's life, followed by long stability. Increasingly, evidence suggests that planetary systems remain dynamic over billions of years. Migration, collisions, and restructuring can occur long after formation. Alpha Centauri's dust may be part of such long-term evolution. It may represent the slow grinding of leftover bodies, the reshaping of orbits, or the influence of planets that have quietly persisted. The phrase, taking shape, can therefore be understood metaphorically but grounded in physics. It refers to ongoing processes that continue to define the system's structure, not to dramatic birth events. The shape being taken is one of balance, of equilibrium among forces rather than of rapid assembly. This idea aligns with the broader theme emerging from Webb's observations. The universe is not a collection of finished products. It is a collection of processes unfolding at different speeds. Some are fast and violent, others are slow and subtle. Alpha Centauri appears to belong to the latter category. For those listening as the day fades or night deepens, there is something reassuring about this picture. Change does not always announce itself with fireworks. Sometimes it persists quietly, shaping outcomes over immense spans of time. Scientists are careful not to overinterpret these hints. The language remains measured. Dust structures are suggestive, not definitive. Worlds are implied, not confirmed, but the implications are taken seriously enough to motivate further observation and modelling. Future studies may refine the picture. Additional Webb observations could map the dust more precisely. Other instruments may search for planetary signals with renewed motivation. Models will be updated to account for the observed structures, exploring how they could arise and persist. What matters now is that Alpha Centauri has shifted categories. It is no longer simply a nearby, well-understood system. It is a system with open questions, with evidence of activity, with hints of complexity that demand explanation. Somewhere within the slow accumulation of data, a realization began to settle in that was more unsettling than any single anomaly. The infrared structures around Alpha Centauri were not just unexpected, they were recognizable. The patterns emerging from the analysis did not feel alien or exotic. Instead, they echoed arrangements scientists knew well, arrangements studied for decades much closer to home. That sense of familiarity is what made the findings uncomfortable in the most productive way. In astronomy, unfamiliar patterns are easy to label as special cases. They can be attributed to unusual histories or rare conditions. Familiar patterns are harder to dismiss. They suggest that what we are seeing nearby may follow rules we already understand, rules that may apply far more broadly than we once assumed. When Alpha Centauri began to resemble something like our own solar system in its debris behaviour, the implications quietly multiplied. The comparison did not come from imagery alone. It came from distribution, temperature gradients, inferred dust mass, and the way emission varied with distance from the stars. When scientists overlaid these characteristics with models of known debris systems, certain alignments stood out. The structures did not mirror our solar system exactly, but they occupied a similar conceptual space. In our solar system, dust is not spread evenly. It concentrates in regions shaped by planets and long-term stability. The zodiacal cloud, a faint band of dust that extends inward from the asteroid belt glows in infrared light. Farther out, the Kuiper belt hosts a reservoir of icy bodies that produce dust through collisions and sublimation. These structures persist because they occupy stable zones maintained by gravitational relationships. What unsettled researchers was that Alpha Centauri's inferred dust appeared to occupy analogous roles, despite the system's very different stellar configuration. Instead of a single sun anchoring everything, there were two. Instead of one dominant gravitational center, there was a shifting balance. Yet the dust did not behave as though it were hopelessly scattered. This raised an immediate question. If familiar debris patterns can emerge and persist in a system as complex as Alpha Centauri, how robust are the processes that create them? Perhaps planetesimal belts are more resilient than models suggested. Perhaps stability does not require simplicity. The discomfort came from proximity. Alpha Centauri is not a distant laboratory where oddities can be quarantined. It is the nearest stellar neighbour. If it hosts structures reminiscent of our own, then the processes shaping our solar system may not be exceptional. They may be common, even in environments once thought hostile to them. The analogy to the zodiacal dust cloud was particularly striking. In our solar system, this dust arises from continuous low-level collisions among asteroids and from cometary activity. It forms a diffuse, warm glow detectable in infrared surveys. The dust inferred around Alpha Centauri produced a glow of similar character, scaled appropriately for the star's luminosities and distances. That similarity does not imply identical composition or origin. Alpha Centauri's dust could differ in grain size, chemistry, or collisional history. But the mere fact that it occupies comparable thermal regimes and spatial scales invites comparison. Such comparisons are not made lightly. Astronomers are acutely aware of the dangers of anthropocentrism, of assuming that what is familiar must be universal. Yet models exist precisely to test whether known processes can operate under different conditions. When those models begin to fit unexpected data, attention sharpens. Another familiar pattern emerged in the asymmetry of the emission. In our solar system, dust distributions are not perfectly uniform. Planetary resonances create clumps and gaps. Jupiter's gravity, for example, shapes the asteroid belt, creating regions of depletion and concentration. Neptune's influence sculpts the Kuiper belt into distinct populations. Alpha Centauri's dust showed hints of similar sculpting, though the agents were less clear. The asymmetries were subtle, not dramatic, but they were consistent with gravitational influence rather than random dispersal. That influence could come from planets, from the star's orbital motion, or from a combination of both. What made this particularly intriguing was that models had predicted such familiarity should not occur so easily. Binary systems were expected to disrupt resonance patterns, to smear out structures rather than maintain them. Yet the data suggested otherwise. This tension between expectation and observation forced a re-examination of assumptions about what binary star systems can support. Perhaps stable niches exist in more places than previously believed. Perhaps the parameter space explored by earlier simulations was too narrow, focusing on worst-case scenarios rather than the full range of possible configurations. The feeling of something being uncomfortably close was not just about distance, it was about implication. If Alpha Centauri exhibits debris behavior analogous to our solar systems, then the line separating familiar from other becomes blurred. Our system stops feeling like a special case and starts looking like one example among many. This has consequences for how scientists think about habitability, not in the immediate sense of life, but in the broader sense of system architecture. Long-lived debris structures imply long-term stability of orbits. Stability is a prerequisite for planets to persist, climates to endure, and environments to evolve. It does not mean that Alpha Centauri hosts Earth-like worlds. It means that the conditions necessary for complex system evolution may not be as rare as once thought, even in multi-star environments. There is also a historical dimension to this familiarity. For centuries, Alpha Centauri has occupied a symbolic place in human thought. It has been the nearest destination in science fiction, the benchmark for interstellar aspiration. Discovering that it may share structural similarities with our own system deepens that symbolic connection in an unexpected way. The unease arises because familiarity reduces distance not just physically, but conceptually. If Alpha Centauri looks more like home than we expected, then the universe feels smaller, not less vast, but more interconnected, governed by shared processes playing out in varied contexts. Scientists responded to this unease with rigour rather than speculation. They tested whether alternative explanations could mimic familiar patterns. Could instrumental biases create apparent structures? Could background subtraction artifacts produce asymmetries? Could stellar variability masquerade as dust emission? Each possibility was examined, each was constrained. None fully accounted for the observed patterns. The conclusion remained provisional but persistent. The dust distribution behaved like a debris environment shaped by long-term dynamics. This does not mean that Alpha Centauri is a mirror of the solar system. The differences remain profound. Two sun-like stars alter radiation fields and gravitational potentials. Stable zones shift over time as the stars orbit each other. Any planets present would experience complex illumination cycles and varying gravitational forces. Yet within that complexity, echoes of familiar behaviour emerge. That combination of difference and similarity is what makes the system so valuable as a case study. It sits at the boundary between what we know well and what challenges our models. The discomfort also extended to how scientists think about detection biases. Many debris disks have been identified around distant stars precisely because they are massive and bright enough to be seen easily. Subtle, low-mass debris environments like our own zodiacal cloud are harder to detect at distance. Alpha Centauri's proximity allows such faint structures to be observed for the first time in another system. This raises a sobering possibility. Our solar system may not be unusually dusty or quiet. It may simply be that we have lacked the sensitivity to detect similar environments elsewhere. Alpha Centauri could be the first of many nearby systems where familiar patterns emerge once we look carefully enough. In that sense, the discomfort is epistemic. It challenges how confident we have been about the rarity or commonness of certain system architectures. It suggests that our observational sample has been skewed toward the obvious, leaving subtlety underrepresented. The familiar pattern also feeds back into theories of planet formation. If debris environments persist in Alpha Centauri, then planetesimal formation must have succeeded at some level. That success implies that the early disk was not entirely disrupted by the binary configuration. It implies that there were windows of stability long enough for solid bodies to grow. Those windows may have been narrower or more transient than in single-star systems, but their existence matters. It expands the range of environments where planets and planetesimals can form. As this realization spread through the community, interest in Alpha Centauri intensified. The system was no longer just nearby, it was illustrative. It became a test case for understanding how universal certain processes truly are. For someone listening late at night, there is a quiet irony here. The closer we look, the less exotic the universe becomes. The stars do not all behave identically, but they often rhyme. Patterns repeat, adapted to context, shaped by local conditions but governed by shared physics. That repetition is comforting and unsettling at the same time. Comforting because it suggests order. Unsettling because it erodes the sense of uniqueness that often underpins our narratives about home. The infrared glow around Alpha Centauri does not declare that there are Earths nearby or civilizations waiting. It does something subtler. It suggests continuity. It suggests that the processes that shaped our own system may be active in our nearest neighbour, even after billions of years. As researchers continue to analyse these patterns, they remain cautious. Familiarity can mislead as easily as novelty. Analogies must be tested, not assumed. Models must be refined to account for binary dynamics. Observations must be extended to confirm stability and persistence. Still, the sense that something close feels uncomfortably familiar lingers. It motivates deeper inquiry rather than complacency. It encourages scientists to question whether their expectations have been too narrow, shaped by convenience rather than completeness. If Alpha Centauri's debris environment resembles ours in key ways, what does that mean for how planetary systems evolve? What assumptions need revisiting? What predictions need updating? Taken together, the quiet glow of dust, the persistence of structure, and the familiarity of the patterns force a reconsideration of something far larger than Alpha Centauri alone. They reach into the foundations of how scientists think planets come into being, how long those processes last, and where they can succeed. What this system suggests is not a rewrite of planet formation theory, but a widening of it, an expansion of what is considered plausible rather than exceptional. For a long time, planet formation was framed as a relatively short and well-defined phase in a star system's life. A star forms. A disk of gas and dust surrounds it. Within a few million years, planets emerge or fail to emerge. The disk dissipates, and the system settles into a long period of relative calm. This picture works well for many single-star systems, and is supported by observations of young stars surrounded by bright protoplanetary disks. Binary systems complicated that picture early on. Simulation showed that having two stars instead of one dramatically alters the gravitational environment. Disks can be truncated, warped, or disrupted. Regions where material can remain stable shrink. In close binaries especially, the assumption took hold that planet formation would be inefficient or rare, particularly near the stars themselves. Alpha Centauri played a quiet role in reinforcing that assumption. Despite its proximity and extensive study, clear evidence for planets around Alpha Centauri A and B remained elusive. Proxima b stood apart, orbiting a distant red dwarf where binary effects were weaker. Over time, the lack of detections around the central pair hardened into expectation. Perhaps planets simply did not form there in significant numbers. The infrared structures Webb revealed now complicate that narrative. Dust does not appear in isolation. It is produced by processes involving solid material, and solid material is the currency of planet formation. Whether or not planets currently exist, the presence of dust implies that planetesimals formed at some point. It implies that the early disk was not completely destroyed before solid bodies could emerge. This realization shifts the focus from whether planets formed to how they formed and what happened afterward. Planet formation is not a single mechanism, but a sequence of stages. Dust grains stick together, aggregates grow, planetesimals emerge. Some become planets, others remain as debris. In binary systems, some stages may proceed efficiently while others stall. The outcome may be fewer planets, smaller planets, or planets on unusual orbits rather than no planets at all. The dust around Alpha Centauri suggests that at least the early stages succeeded. Planetesimals must have formed in sufficient numbers to supply a debris environment billions of years later. That alone expands the range of environments where planet formation is considered viable. Another implication concerns timing. If debris persists, it suggests that collisional processes are ongoing. That means the system is not simply preserving ancient remnants, but actively reshaping itself. Planet formation, in this broader sense, may be less confined to the system's youth than once believed. There is growing evidence from other systems that planetary architectures can evolve long after formation. Planets migrate, orbits destabilize, late collisions occur, debris disks flare up and fade. Alpha Centauri's dust could be part of such long-term evolution rather than a fossil from the distant past. This perspective reframes planet formation as a continuum rather than a chapter with a clear ending. In that continuum, binary systems may follow different paths, but they are not excluded from participation. The spatial distribution of the dust matters here. If it occupies regions predicted to be marginally stable, that suggests that the system's architecture may have evolved to accommodate material there. Planets, if present, could play a role by carving out niches where debris can persist. Alternatively, the star's orbital dynamics may create time-average stability zones not captured by simpler models. Either way, the data imply that our theoretical boundaries for planet formation may be too rigid. Another aspect worth considering is mass. The amount of dust inferred around Alpha Centauri is modest, but that does not mean the underlying population of solid bodies is small. Dust represents only the tiniest fraction of mass in a debris environment. Most of the mass resides in larger bodies that do not emit strongly in infrared. A faint glow can mask a substantial reservoir of solid material. This matters because planet formation efficiency depends on how much material is available and how it is distributed. Even if only a small fraction of planetesimals ever become planets, the existence of a reservoir increases the odds. It also raises questions about detection bias. Many of our constraints on planet formation in binary systems come from systems where planets have been detected directly. Those detections favour certain configurations and masses. Subtler systems may simply evade current methods. Dust becomes an indirect probe, revealing what planets cannot yet. Alpha Centauri's case suggests that absence of evidence should not be overinterpreted as evidence of absence, especially in complex systems. There's also the matter of composition. The spectral characteristics of the dust hint at silicate-rich material, similar to what is found in rocky debris. While this does not prove the existence of rocky planets, it aligns with conditions under which such planets could form. It suggests that the building blocks of terrestrial worlds were present at some stage. This has implications for habitability research, though cautiously so. Habitability depends on many factors beyond planet formation, including stellar activity, orbital stability, and atmospheric evolution. Alpha Centauri A and B are relatively stable stars, similar to the Sun. If planets formed there and survived, they could, in principle, occupy environments not wildly dissimilar from those in our own system. Again, this is not a claim, but a possibility reopened by the data. Another shift concerns the role of binaries in planet formation statistics. Surveys suggest that a significant fraction of stars are in multiple systems. If planet formation were severely suppressed in such environments, planets would be rarer than observed. The growing catalogue of exoplanets in binary and even triple systems already hints that formation is more adaptable than early models predicted. Alpha Centauri adds weight to that adaptability. It suggests that even close binaries may support the processes needed to build and maintain complex architectures. This adaptability may arise from self-organization. Disks respond to gravitational forces by redistributing material. Regions of instability clear quickly, leaving behind pockets where growth can proceed. Over time, these pockets may dominate the system's long-term behavior. The presence of dust structures around Alpha Centauri implies that such pockets existed and perhaps still exist. Understanding where they are and how they form becomes a priority for refining planet formation theory. Theoretical work is already responding. Models are being updated to explore wider ranges of initial conditions, stellar mass ratios, orbital eccentricities, and disk properties. Instead of asking whether planet formation is possible in binaries, researchers are asking under what conditions it thrives or fails. Alpha Centauri provides a concrete anchor for these questions. Its properties are well measured. Its age is constrained. Its stellar orbits are known. Any successful model must account for its observed environment. There is also a philosophical shift embedded here. Planet formation theory has often been guided by the desire to explain our own system. That focus is natural, but it can bias assumptions. Observations like these remind scientists that nature explores possibilities beyond our intuitive preferences. Our solar system may be one outcome among many. Alpha Centauri may represent another, shaped by similar physics but different constraints. For listeners easing toward rest, there is a gentle reassurance in this idea. Complexity does not require perfection. Systems can form worlds even under challenging conditions. Order can emerge from environments that look, at first glance, hostile to it. The data do not suggest a system teeming with planets. They suggest a system that did not simply fail. That distinction matters. It means that binary systems should not be dismissed in searches for planets or in theories of system evolution. Future observations will refine this picture. More sensitive measurements may detect planets directly. Continued infrared monitoring may reveal changes in the dust distribution. Comparative studies of other nearby binaries may reveal whether Alpha Centauri is typical or exceptional. What is already clear is that planet formation theory can no longer afford to ignore subtle evidence. Dust, once treated as a nuisance or a footnote, has become a central character. It tells a story of persistence, interaction, and possibility. That story does not end with formation. It extends into how systems age, how they rearrange themselves, and how long they remain dynamic. Alpha Centauri's glow suggests that even after billions of years, the processes that shape planetary environments have not entirely gone quiet. As scientists absorb these implications, they are forced to confront the limits of earlier assumptions. The comfortable boundaries around where planets can form and persist are being pushed outward, made fuzzier, less absolute. That discomfort is productive. It encourages humility and curiosity. It invites deeper exploration rather than premature closure. From the moment the word planet enters the conversation, another question tends to follow quietly behind it, whether or not anyone says it out loud. Could any of those worlds support conditions even remotely friendly to life? In the case of Alpha Centauri, that question carries extra weight. Not because of optimism or science fiction, but because of proximity. When something is this close, the idea of habitability feels less abstract, less safely distant. Yet this is where scientists slow down even more. Habitable does not mean inhabited. It does not mean Earth-like. It does not even mean pleasant. In scientific terms, habitability is a narrow, careful concept, tied primarily to whether liquid water could exist on a planet's surface for extended periods of time. Even that definition is a simplification, but it provides a starting point grounded in chemistry and physics rather than imagination. Alpha Centauri complicates the habitability question before planets even enter the picture. With multiple stars, illumination changes over time. Gravitational forces vary. Stable orbits exist, but they are constrained. Any potentially habitable world would need to survive not just its host star, but the influence of its stellar companions over billions of years. For Alpha Centauri A and B, the situation is nuanced. Each star has a region around it where liquid water could, in principle, exist on a planetary surface. These regions depend on stellar luminosity and planetary distance. Alpha Centauri A, being slightly brighter than the Sun, would have a habitable zone located a bit farther out. Alpha Centauri B, dimmer and cooler, would host such a zone closer in. The challenge is stability. In a binary system, not all orbits are long-lived. For a planet to remain habitable, its orbit must be stable over geological timescales. Simulations suggest that planets orbiting close to one star in a binary, in what are called circumstellar or S-type orbits, can remain stable if they stay well within a certain distance from their host star. For Alpha Centauri A and B, those stable zones do overlap with their respective habitable zones, at least in principle. This has been known for years and is one reason the system has remained of interest despite the lack of confirmed planets. Stability alone, however, is not enough. Habitability also depends on stellar behaviour. Both Alpha Centauri A and B are relatively calm stars compared to many others. They do not flare violently like red dwarfs. Their radiation environments are more predictable. This works in their favour. Long-term climatic stability requires not just a stable orbit, but a relatively stable star. In this respect, Alpha Centauri A is particularly appealing. Its similarity to the Sun extends beyond mass and temperature. Its variability, magnetic activity and lifespan all resemble what we see in our own star. If a planet were to exist in its habitable zone, the stellar conditions would not be immediately disqualifying. Alpha Centauri B presents a slightly harsher environment, but still remains within the range considered potentially habitable by stellar standards. Neither star emits the intense frequent radiation bursts that plague many smaller stars. The presence of dust and debris adds another layer to this discussion. On one hand, debris environments imply collisions. Collisions can be destructive, especially for developing or existing planets. Heavy bombardment can sterilize surfaces repeatedly. On the other hand, impacts can also deliver water and organic material, as is thought to have happened on Earth. In our own solar system, the early heavy bombardment likely played a role in shaping Earth's oceans and chemistry. A debris-rich environment is not automatically hostile to habitability. The timing, intensity and duration of impact matter far more than their mere existence. The infrared structures observed around Alpha Centauri suggest ongoing but low-level activity rather than catastrophic instability. This distinction is crucial. A gentle collisional environment can coexist with habitable conditions. A violent one cannot. There is also the question of atmospheric retention. Planets in binary systems may experience additional gravitational perturbations that influence their rotation, axial tilt, and orbital eccentricity. These factors affect climate stability. Large variations in eccentricity can drive extreme temperature swings, challenging habitability. However, simulations indicate that planets in stable circumstellar orbits around Alpha Centauri A or B could maintain relatively circular orbits, especially if they formed in situ or migrated gently. Again, this does not guarantee habitability, but it does not rule it out either. Proxima Centauri complicates the narrative in a different way. Proxima B orbits within its star's habitable zone by distance, but Proxima is a red dwarf with frequent flares. That raises concerns about atmospheric erosion and surface radiation. Despite that, Proxima B remains one of the most discussed potentially habitable exoplanets simply because it exists and is close. The contrast between Proxima B and hypothetical planets around Alpha Centauri A or B highlights an important point. Habitability is a spectrum, not a binary label. Different environments present different challenges and advantages. A planet around Alpha Centauri A might enjoy a calmer star but face binary dynamics. A planet around Proxima faces stellar activity but simpler orbital mechanics. The dust structures observed around the central binary subtly reopen the door to these considerations. They suggest that solid material existed and persisted long enough for planets to form. They suggest that the system's architecture did not preclude complexity. That alone is enough to warrant renewed attention. Yet scientists remain cautious for good reason. Dust does not equal planets. Stable zones do not equal habitability. Even confirmed planets do not equal life. Each step adds uncertainty rather than removing it. What changes with Webb's observations is not the conclusion, but the prior probability. Before, the lack of evidence leaned heavily towards skepticism. Now, the balance shifts slightly toward openness. The system is no longer assumed barren by default. This shift influences how future observations are prioritized. Alpha Centauri becomes a more attractive target for high-precision radial velocity surveys, direct imaging efforts, and long-term monitoring. Not because it promises habitable worlds, but because it no longer contradicts the possibility. There is also a broader implication. If a nearby binary system can host debris structures and possibly planets, then the inventory of potentially habitable environments in the galaxy expands. Binary systems are common. If even a fraction of them support habitable planets, the total number of such worlds increases significantly. This has consequences for how scientists think about life's potential distribution. It does not suggest that life is common, but it removes one class of systems from automatic exclusion. For someone listening late into the night, there is a quiet tension here between restraint and wonder. The data invite curiosity, but they also demand discipline. Scientists resist the urge to leap from dust to oceans, from infrared glow to biology. Instead, they focus on refining constraints. How stable are the inferred dust structures? How much mass do they represent? What configurations of planets could produce them? How do binary dynamics influence long-term climate stability? Each question leads to another, and none has a simple answer. It is also worth noting that habitability is not static. A planet may pass through habitable phases during its lifetime. Binary dynamics could induce cycles, periods of relative stability punctuated by change. Life, if it arises, may adapt or retreat. Habitability is as much about duration as it is about conditions. Alpha Centauri's age suggests that if habitable conditions ever existed, they had time to persist. That is neither comforting nor alarming, it is simply context. What makes this system compelling is not that it promises answers, but that it refuses to close the door. It remains ambiguous in a way that is scientifically valuable. As research continues, scientists will likely frame Alpha Centauri not as a prime target for finding life, but as a testbed for understanding habitability in complex systems. Its proximity allows detailed study. Its binary nature challenges models. Its dust environment provides clues. Together, these factors make it a laboratory rather than a destination. The question of habitable worlds nearby therefore remains open, but better informed. It is no longer a speculative aside. It is a structured inquiry guided by observation, theory, and restraint. And as that inquiry deepens, it begins to press against assumptions that have guided the field for decades. Assumptions about where planets can form, about how long systems remain active, about how complexity arises and persists. For decades, the picture felt settled enough to stop questioning. Binary star systems, especially close ones, were treated as complicated but ultimately limiting environments, places where planet formation struggled, debris cleared quickly, and long-term calm arrived sooner rather than later. That framework did not come from laziness or lack of imagination. It emerged from simulations, from partial observations, and from the understandable desire to simplify a universe that already offers more complexity than any one theory can comfortably hold. What the James Webb observations of Alpha Centauri did was not overturn that framework in a single stroke. Instead, they pressed on its weakest seams. They revealed where assumptions had hardened into expectations, and where expectations had quietly narrowed the range of outcomes scientists were willing to consider. One of the oldest assumptions challenged by these findings concerns efficiency. For a long time, it was believed that binary systems were inefficient builders of planetary architecture. The reasoning was straightforward. Two stars introduce competing gravitational influences. Disks are truncated. Material is stirred violently. Collisions become destructive rather than constructive. Under those conditions, forming and retaining planets seemed unlikely, especially in regions close to the stars. This assumption was never absolute, but it carried weight. It shaped how observational results were interpreted. When planets were not detected around Alpha Centauri A or B, it felt consistent with theory rather than surprising. The absence reinforced the narrative, and the narrative reduced the urgency to look deeper. The infrared dust structures Webb detected quietly undermine that logic. Dust is evidence of inefficiency only if one assumes that systems should be empty by now. If instead, systems can maintain long-lived reservoirs of solid material through slow replenishment, then inefficiency becomes relative rather than absolute. The system may not build planets as easily as a single star system, but it may still build enough to matter. Another challenged assumption lies in timing. Planet formation was long treated as something that either succeeds early or fails permanently. In that view, a mature system like Alpha Centauri should reflect the outcome clearly. Either planets formed and remained detectable, or they did not, leaving little behind. The persistence of dust complicates this binary outcome. It suggests that activity continues, that interactions among solid bodies did not cease once the early disk vanished. This implies that planet formation and system evolution are not neatly partitioned into early and late phases. Instead, they may overlap, with late-stage processes reshaping architectures long after initial formation. This challenges the idea that the absence of early success implies permanent failure. A system may form planetesimals early, stall at planet formation, and yet remain dynamically active, retaining the capacity to build or reshape worlds later under the right conditions. A third assumption under pressure concerns stability zones. Classical models defined regions around stars where orbits would remain stable and regions where they would not. In binary systems, these zones were often drawn conservatively, emphasizing where stability was guaranteed rather than where it was merely possible. The dust observed around Alpha Centauri appears in regions that lie near or even beyond those conservative boundaries. That does not mean the models were wrong, but it does suggest they were incomplete. Stability may not be a simple yes or no condition. It may exist on a spectrum, with some regions supporting material over long timescales through complex balancing of forces. In other words, what was once labelled unstable may actually be conditionally stable, depending on particle size, replenishment rates, resonant interactions, and time-averaged dynamics. The universe does not always respect the clean lines we draw in parameter space. There is also an assumption about simplicity at play. Mature systems were often imagined as simpler than young ones, stripped of complexity by time. Dust disks, clumps, and asymmetries were associated with youth. Age was equated with tidiness. Alpha Centauri challenges that aesthetic expectation. Its dust structures are not chaotic, but they are not absent either. They suggest that complexity can persist quietly, maintained by slow processes rather than dramatic events. Age, in this context, does not guarantee simplicity. It guarantees history. Another deeply ingrained assumption concerns observational absence. For decades, astronomers relied heavily on what they could not see. If no dust was detected, it was assumed absent. If no planets were detected, it was assumed unlikely. This was not unreasonable given instrumental limits, but it created a feedback loop. Systems that did not announce themselves loudly faded into the background of scientific attention. Webb disrupts that loop by revealing what was previously invisible. The dust around Alpha Centauri did not suddenly appear. Our ability to detect it did. This forces a re-evaluation of how many other systems may harbour subtle features that simply lie below past detection thresholds. The implication is uncomfortable. It suggests that some conclusions drawn from non-detections may need revisiting, not because they were careless, but because they were constrained. Another challenged assumption involves universality. Planet formation models have often been calibrated against a limited set of observationally accessible systems. Those systems tended to be either young and bright or massive and dramatic. Quiet, subtle systems like Alpha Centauri's mature environment were underrepresented. The Webb findings suggest that our sample may have been biased toward extremes. If subtle debris environments are common but hard to detect, then our understanding of what a typical planetary system looks like may be skewed. This bias matters because theories are shaped by examples. If the examples are incomplete, the theories will reflect that incompleteness. There is also a sociological layer to these assumptions. Alpha Centauri's familiarity bred a certain complacency. It was nearby, well studied, catalogued. It did not feel like a place where surprises waited. That perception influenced research priorities in subtle ways. The new data disrupt that comfort. They remind scientists that familiarity does not equal exhaustion. Even the most studied systems can reveal new facets when viewed differently. Importantly, these challenged assumptions do not collapse under scrutiny. They bend. Binary systems are still challenging environments. Planet formation may still be less efficient there on average. Stability zones still matter. Youth still correlates with activity. What changes is the rigidity of these ideas. They become guidelines rather than rules. The process by which this happens is instructive. Scientists did not discard old models impulsively. They compared them carefully with new data. They asked whether small adjustments could reconcile theory and observation. They explored whether alternative explanations could preserve existing frameworks. Only when the discrepancies persisted did the conversation shift from adjustment to reconsideration. This is how science evolves, not through sudden revolutions in every case, but through accumulated pressure that makes old positions harder to defend without modification. Alpha Centauri's dust does not demand a new theory of planet formation. It demands humility. It demands that models accommodate a broader range of outcomes. It demands that uncertainty be acknowledged where certainty once felt comfortable. For listeners drifting deeper into rest, there is a gentle lesson here beyond astronomy. Knowledge advances not by clinging to what feels tidy, but by making room for what feels slightly wrong. The universe rarely breaks our rules outright. It stretches them. The old assumptions served their purpose. They guided inquiry when data were sparse. They provided a framework for interpretation. Now, richer data invite richer frameworks. This shift has practical consequences. It influences which systems are targeted for future observation. It shapes how simulation parameters are chosen. It affects how confidently scientists can rule out certain scenarios. Alpha Centauri moves from the category of probably uninteresting in this respect to informative precisely because it challenges expectations. That is a significant reclassification. It also has implications for how scientists communicate uncertainty. The temptation to present clean narratives is strong, especially when explaining complex topics to broad audiences. Findings like these resist such narratives. They are nuanced, conditional, and evolving. Communicating that nuance without overstating or understating significance is part of the challenge. As the field absorbs these implications, old assumptions give way to revised questions. Instead of asking whether binary systems can form planets, scientists ask under what conditions they do so efficiently. Instead of assuming mature systems are quiet, they ask what processes sustain low-level activity over long timescales. These are better questions, not because they promise easier answers, but because they align more closely with what the universe appears to be doing. Alpha Centauri's quiet glow has not shattered understanding. It has refined it. It has exposed where confidence exceeded evidence and where caution is now warranted. Even with all the new data in hand, perhaps the most honest thing scientists can say about Alpha Centauri right now is that much of it remains unresolved. The James Webb observations clarified certain questions, but they also exposed how many layers of uncertainty still sit beneath what looks, at first glance, like a simple nearby system. Understanding has advanced, but it has not closed the book. Instead, it has opened several pages at once, each filled with careful questions rather than firm answers. One of the most immediate uncertainties concerns the precise nature of the dust itself. Infrared observations can tell scientists a great deal, but they do not provide a complete inventory. The glow detected around Alpha Centauri is consistent with dust, but dust is not a single thing. Grain size matters, composition matters, shape matters. A population dominated by micron-sized grains behaves very differently from one dominated by larger fragments. Radiation pressure affects them differently. Collisional lifetimes differ. Thermal emission profiles shift subtly depending on mineralogy. At present, scientists can constrain ranges, but not pin down exact distributions. Are the grains primarily rocky silicates, similar to asteroid dust? Do they include significant icy components? Are they porous aggregates or compact fragments? Each possibility points toward a different origin story and a different evolutionary pathway. Related to this is the question of replenishment. Dust does not last. Individual grains are removed on timescales far shorter than the age of the system. If dust is present now, something must be making more of it. But what exactly is doing that work? One possibility is a steady collisional cascade among a belt of planetesimals. Another is a more episodic process, perhaps triggered by a recent destabilization event that increased collision rates temporarily. Distinguishing between steady state and transient scenarios is difficult with limited temporal coverage. Webb's observations provide a snapshot, not a movie. Time matters here. A debris environment sustained for millions or billions of years implies a stable reservoir of larger bodies. A transient cloud could fade on much shorter timescales. Without long-term monitoring, scientists must rely on indirect clues, such as dust mass estimates and grain lifetimes, to infer which scenario is more likely. Another unresolved issue lies in spatial structure. The inferred distribution of dust suggests organization, but the resolution limits of current data leave room for multiple interpretations. Are there one or more distinct belts? Are there gaps indicative of planetary influence? Is the dust primarily circumstellar, orbiting one star, or circumbinary, influenced by both? In a system like Alpha Centauri, these distinctions are subtle but critical. Circumstellar disks around each star would imply relatively isolated environments. A circumbinary structure would imply material responding to the combined gravitational field. Each scenario carries different implications for stability, replenishment, and planet formation. Current models can reproduce aspects of the observed emission under different assumptions, but degeneracy remains. Different configurations can produce similar infrared signatures. Breaking that degeneracy requires additional data, possibly at other wavelengths, or with different observing geometries. Then there is the role of planets, which remains entirely inferential at this stage. Dust structures often point toward planetary sculptors, but no planets around Alpha Centauri A or B have been confirmed. This absence is itself ambiguous. It could mean planets are rare or absent. It could mean they are small, distant, or oriented in ways that make them hard to detect. Scientists are trying to understand how massive a planet would need to be to produce the observed dust patterns. Could an Earth-mass planet suffice, or would a larger body be required? Could multiple smaller planets act collectively? How would binary dynamics modify their influence? These questions push the limits of current modelling. Planet-dust interactions in single-star systems are already complex. Add a second star, and the parameter space expands dramatically. Simulations must account for time-varying gravitational potentials, resonances that shift as stars orbit each other, and long-term secular effects. Another layer of uncertainty involves the stars themselves. Stellar winds, magnetic activity, and radiation output influence dust dynamics. While Alpha Centauri A and B are relatively well characterized, subtle variations over time could affect the dust environment. Small changes in stellar activity can alter grain lifetimes and distribution. The interaction between the stars' radiation fields is also not fully understood. Dust grains experience combined illumination from two sources whose relative positions change over time. This leads to complex heating patterns that may not be captured fully by simplified models. Proxima Centauri adds still more complexity. Although distant, its gravitational influence is not negligible over very long timescales. Could Proxima's orbit perturb outer debris reservoirs, injecting material inward or altering stability zones? Over billions of years, even weak influences can accumulate. Scientists are actively exploring these long-term dynamical questions. They require simulations that run over immense timescales, with high precision, a computationally demanding task. Simplifications are unavoidable, but each simplification risks missing subtle but important effects. There is also uncertainty about how representative Alpha Centauri is. Is it unusual, or merely the first nearby system where subtle debris has been detected? Without a comparative sample, it is difficult to say. Webb's sensitivity makes it possible to study similar nearby systems, but such observations take time and careful planning. If other nearby binaries show similar infrared signatures, it would suggest that Alpha Centauri is typical. If not, it may be an outlier shaped by a unique formation history. Both outcomes would be informative, but they lead to different conclusions about planet formation and system evolution. Another unresolved question involves initial conditions. Alpha Centauri formed billions of years ago under conditions that are difficult to reconstruct. The mass and structure of its original protoplanetary disk, the timing of stellar interactions, and the early dynamical history all influence present-day outcomes. Without direct observation of those early stages, scientists must infer backward from current structures. This inverse problem is notoriously difficult. Many different histories can lead to similar present configurations. Narrowing the range requires combining observational constraints with statistical reasoning and population studies. There is also the matter of observational bias. Webb's detection capabilities are extraordinary, but not uniform across all conditions. Bright nearby stars pose challenges. Certain configurations may be easier to detect than others. Understanding what Webb might miss is as important as understanding what it reveals. Scientists are keenly aware of this. They invest significant effort in characterizing detection limits, testing whether certain dust distributions would remain invisible even to Webb. This helps avoid overconfidence and guides future observational strategies. The question of habitability, while compelling, remains particularly uncertain. Even if planets exist and debris persists, translating that into habitable conditions involves many additional variables. Atmospheric composition, magnetic fields, geological activity, and orbital evolution all matter. Alpha Centauri's binary nature could induce climate variability on any planets present. Whether such variability would be harmful or merely different depends on details that are currently inaccessible. Scientists can model scenarios, but without direct planetary data, these remain speculative. There is also uncertainty about timescales. Habitability is not a momentary state. It requires stability over long periods. A planet might pass through habitable conditions briefly, without ever allowing life to take hold. Understanding these durations is challenging even for Earth, let alone distant worlds. Another area of active inquiry concerns comparison with the solar system. How similar is Alpha Centauri's debris environment really? Superficial similarities may mask deeper differences. Dust mass, grain properties, and spatial distribution all need to be compared carefully to avoid misleading analogies. Scientists are cautious about overextending the familiarity narrative. They recognize that similarity in one metric does not guarantee similarity in others. The challenge lies in identifying which similarities are meaningful and which are coincidental. Theoretical frameworks are evolving in response to these uncertainties. Instead of seeking definitive answers, researchers are building flexible models that can accommodate a range of outcomes. These models are tested against data, refined, and tested again. This iterative process takes time. It does not produce dramatic announcements. It produces gradual shifts in understanding. Alpha Centauri's case exemplifies this mode of science. The findings are not a conclusion, but a prompt. There is also an institutional dimension to what scientists are still trying to understand. Telescope time is limited. Research priorities compete. Deciding how much attention Alpha Centauri deserves relative to other targets involves judgment calls informed by evolving evidence. As the picture grows more complex, arguments for continued observation strengthen. Yet those observations must be designed carefully to address specific uncertainties rather than simply gather more data. Future Webb observations may target different wavelengths, different viewing angles, or different times in the star's orbit. Other instruments may complement Webb by probing different aspects of the system. Ground-based observatories may refine stellar parameters or search for planetary signals with improved techniques. All of this reflects a broader truth about science. Understanding is not a destination. It is a process shaped by questions as much as by answers. The more clearly scientists see, the more sharply they perceive what remains unseen. Alpha Centauri has moved from a system thought to be well understood to one recognized as subtly complex. That recognition does not diminish previous knowledge, it contextualizes it. For someone listening in a quiet moment, there is something fitting about this state of partial understanding. The universe does not rush to explain itself. It reveals hints, patterns, and contradictions, inviting patience rather than certainty. Scientists are still trying to understand how dust persists where it should not. They are still trying to understand what unseen structures may shape it. They are still trying to understand how general these findings are, and what they imply for planetary systems as a whole. These open questions are not signs of failure, they are signs of progress. They mark the boundary between what was assumed and what must now be explored. After everything that has been measured, modelled, debated, and left unresolved, it becomes natural to lift the gaze outward again, away from instruments and data and back toward the sky itself, not in search of new evidence this time, but in search of perspective. Alpha Centauri has not changed in brightness. It has not moved closer in any way that matters physically. And yet, understanding has a way of shortening distances that space itself keeps vast. For most people, Alpha Centauri remains invisible to the naked eye unless viewed from the southern hemisphere, and even then it appears as a simple point of light, easy to overlook among brighter stars. There is no obvious sign, no visual cue that anything subtle or complex surrounds it. No hint of dust, no trace of structure, no suggestion of activity, just light, steady, and unassuming. What has changed is not the star system, but our relationship to it. Knowing that Alpha Centauri is not merely a quiet pair of suns drifting through space, but a system with structure, history, and ongoing processes, reshapes how it occupies the imagination. It becomes less like a distant marker and more like a place, not in the sense of destination, but in the sense of context, a neighbouring environment governed by the same physical rules that shape our own. This return to the night sky does not undo the complexity revealed by James Webb. It absorbs it. The dust, the infrared glow, the unresolved questions all settle into the background of awareness rather than demanding constant attention. They become part of what the star quietly carries with it as it rises and sets. There is something grounding about that. Astronomy often moves in two directions at once. One direction pushes deeper into detail, into spectra, simulations and uncertainty ranges. The other pulls back, reminding us that all of this complexity exists within a sky that people have watched for thousands of years without knowing any of it. Neither direction is complete on its own. When you look up now, whether literally or in memory, Alpha Centauri can hold both meanings at once. It can be the nearest stellar neighbour and a system still resisting full explanation. It can be familiar and unsettled. It can be simple to see and difficult to understand. That tension is not something to resolve. It is something to rest with. Much of the shock surrounding Webb's observations came from the realization that closeness does not guarantee understanding. Distance had always been a convenient explanation for ignorance. Of course we don't know much about distant stars, they're far away. Alpha Centauri removes that excuse. It sits close enough that surprise feels almost personal. And yet, that surprise was gentle. No alarms were raised. No urgent revisions were demanded overnight. Instead, a quiet adjustment took place. Models were revisited. Assumptions softened. Confidence gave way to curiosity. This is science at its most human, not driven by spectacle, but by humility. Returning to the night sky with this knowledge does not require remembering technical details. You do not need to recall dust temperatures or stability zones. You do not need to keep track of unresolved parameters. All of that can fade safely into the background. What remains is a subtle shift in how the sky feels. Stars stop being mere reference points. They become systems with interiors, with histories still unfolding, with processes that continue even when no one is watching. Alpha Centauri becomes less of a boundary marker and more of a reminder that the universe nearby is just as layered as the universe far away. There is also comfort in how incomplete the story remains. If Webb had revealed a definitive answer, something clean and final, the sense of closeness might feel finished. Instead, the open questions leave space. Space for future observation, space for reinterpretation, space for imagination grounded in restraint rather than speculation. This openness is important. It keeps Alpha Centauri from becoming a solved problem. It remains an invitation rather than a conclusion. From Earth, nothing about the star system signals this complexity. Light still takes just over 4 years to arrive. The stars still move across the sky according to predictable patterns. Their presence remains steady, unchanged by our improved understanding. That steadiness is reassuring. It reminds us that knowledge does not alter the universe. It alters our relationship to it. There is a parallel here that does not need to be emphasized, but can be felt. Many things close to us feel familiar until we look carefully. Many assumptions hold until better tools reveal what was always there. The universe is not unique in that regard. Alpha Centauri's dust was not created by our observation. It existed quietly long before Webb. It will continue to exist, or fade, or rearrange itself, regardless of whether it is being studied. That indifference is not cold. It is simply honest. As the mind settles, the story does not end with a declaration or a takeaway. It slows, it widens again. The technical narrative gives way to a broader awareness of scale, time, and patience. Science often advances through moments like this, where something small but persistent refuses to fit neatly. Those moments rarely feel dramatic in real time. They feel like mild discomfort, like an itch at the edge of certainty. Over time, they reshape frameworks more effectively than revolutions ever could. Alpha Centauri now occupies that space, not as a mystery in need of solving immediately, but as a reminder that even our nearest neighbours can still surprise us when we finally listen carefully enough. Looking up, or simply imagining the sky, you do not need to feel excitement or anticipation. It is enough to feel continuity. The same processes shaping distant galaxies are shaping nearby systems. The same patience required to understand them applies everywhere. There is no urgency in this story. Webb will continue to observe. Scientists will continue to model. Data will accumulate slowly. Interpretations will evolve. None of this needs to resolve tonight. For now, Alpha Centauri can return to being a quiet presence, carrying its complexity without demanding attention. It does not need to be watched constantly to matter. Its proximity alone ensures that it remains part of our cosmic neighbourhood, whether or not we fully understand it. In that sense, it feels a little closer than before, not because the distance has changed, but because the gap between what we assumed and what we now allow ourselves to question has narrowed. That narrowing is subtle, almost imperceptible, but it alters perspective all the same. As the night continues and attention softens, the sky does not ask to be analysed. It simply exists. Stars hold their light. Systems evolve quietly. Understanding follows when it can, at its own pace. And with that awareness, there is no need to conclude, no need to summarise, no need to close the story. The universe does not end its narratives cleanly. It lets them drift, overlap, and continue. So the gaze remains upward, not fixed, not searching, just present. Alpha Centauri stays where it has always been, nearby in cosmic terms, distant in human ones, and now carrying just a little more meaning than it did before, without needing to announce it at all.